The 1 equals 2 trick. Imagine sitting quietly at a desk late at night, the world around you fading into darkness. You pick up a pen and paper and begin to follow a seemingly simple algebraic proof. Step by step, you move through equations with confidence. Suddenly, the final line stares back at you. 1 equals 2. The impossible has happened. Your logical mind reels. How can this be? What did you miss? You check again. The math appears flawless, yet the conclusion defies everything you know. This is the essence of the 1 equals 2 trick. At its heart, this trick is a clever manipulation of mathematical rules, a sleight of hand that exploits hidden assumptions and subtle errors. It's a paradox wrapped in elegant equations, designed to challenge the certainty we place in arithmetic, the foundation of all logic. The trick works because mathematics, like language, relies on strict rules. If any step breaks these rules, even invisibly, the entire structure collapses. The 1 equals 2 proof often hides a division by 0, an illegal move that distorts the logic. Yet, this critical flaw is camouflaged within the steps, making it nearly invisible at first glance. Why does this matter beyond math class? Because it reveals something profound about how we understand truth and certainty. If a simple trick can prove such an absurdity, what does that say about the limits of logic? What cracks lie hidden beneath the surface of the systems we trust? This paradox shakes the foundation of confidence. It invites a deep, unsettling doubt, not only about numbers, but about the nature of knowledge itself. It whispers that reality may be more fragile and complex than it seems. In philosophy, similar paradoxes abound. The liar's paradox, this statement is false, loops endlessly, defying resolution. Gödel's incompleteness theorems reveal that in any complex system, some truths are unprovable. These puzzles highlight the limits of formal logic and the mysteries at the edges of certainty. The 1 equals 2 trick embodies this tension perfectly. It's a playful demonstration that even in the rigid realm of mathematics, errors and illusions can emerge, inviting us to question and explore deeper. For students, mathematicians, and thinkers, this trick is both a warning and a lesson. It warns against blind acceptance, urging careful scrutiny of every step and assumption. It teaches humility, reminding us that knowledge is built on foundations that must be continually examined. The late-night effect, questioning all arithmetic after midnight, is more than fatigue. It is the mind grappling with the fragile boundary between certainty and illusion. It's the cognitive dissonance sparked by a paradox that defies easy resolution. Yet, this paradox also inspires curiosity. It pushes us to refine our understanding, to seek clarity in complexity. It fuels the pursuit of rigor, precision, and deeper insight. In life, too, we encounter 1 equals 2 moments, situations where appearances deceive, where logic falters, and where what we believe to be true is challenged. The trick teaches resilience in the face of uncertainty and the courage to question the unquestionable. So, next time you see a proof that seems too strange to be real, remember the 1 equals 2 trick. Look closely for hidden flaws. Embrace the mystery it reveals, and carry forward the lesson that truth, like math, demands both wonder and rigor. The infinity subtraction collapse. The concept of infinity has fascinated and baffled humanity for millennia. It is an idea so vast, so beyond ordinary experience, that it challenges the very foundations of mathematics, philosophy, and logic. Among the many paradoxes that arise when we attempt to understand infinity, one of the most confounding is the question, what happens when you subtract infinity from infinity? Intuitively, subtraction means taking away, reducing quantity, making something smaller. But when the quantities involved are infinite, the operation defies the rules we rely on in the finite world. Infinity minus infinity could equal 0. It could equal another infinity, or it might be entirely undefined. This paradox, the infinity subtraction collapse, tears at the fabric of certainty, forcing us to confront the limits of reason itself. To begin unpacking this, we need to understand what infinity really means in mathematics. Infinity is not a number you can reach or count to. It is a concept describing something that is unbounded, limitless, and never-ending. In the realm of numbers, we talk about different sizes or types of infinity. The set of all natural numbers, 1, 2, 3, and so forth, extends infinitely. But surprisingly, the set of even numbers, 2, 4, 6, and so on, is also infinite. Yet both sets are considered to have the same cardinality, meaning they are equally infinite in size, even though one is a proper subset of the other. This counterintuitive idea was formalized by the mathematician Georg Cantor in the late 19th century, who revolutionized our understanding of infinite sets. Now, imagine subtracting one infinite set from another. Consider taking the infinite set of even numbers away from the infinite set of natural numbers. What remains is the set of odd numbers, which is also infinite. So, here, infinity minus infinity equals infinity. But if you try subtracting other infinite sets, you can get different answers. For example, if you take the infinite set of natural numbers and subtract the exact same infinite set, you might expect 0, since everything has been removed. Yet, in some mathematical frameworks, this subtraction is considered undefined, because infinity is not a number that behaves like finite numbers. This ambiguity stems from the fact that infinite quantities do not obey the usual arithmetic rules. When dealing with finite numbers, subtraction is straightforward. Take away a certain amount and the remainder is clear. But infinity is not fixed or concrete. It is a concept that defies finite measurement. The operation of subtracting infinity from infinity lacks a unique, well-defined outcome. It depends on the context, the nature of the sets involved, and the way subtraction is defined. One vivid analogy to illustrate this paradox is to think of two infinite strings of beads. If you remove one infinite string of beads from another identical infinite string, how many beads remain? The intuitive answer might be none, 0 beads. But since both strings are infinite, the process of removal can be matched bead for bead, leaving no beads behind. Alternatively, if the beads are arranged differently, or if you remove beads in a certain pattern, you might be left with another infinite string of beads. Or the operation may be considered nonsensical altogether. This shows how infinity does not yield to our standard operations. In calculus and analysis, these ambiguities manifest in limits involving expressions like infinity minus infinity. When evaluating functions that tend toward infinity, the expression infinity minus infinity appears frequently as an indeterminate form. This means it does not have a unique limit and requires further analysis to resolve. For example, the function f of x equals sine x and gx equals sine x. Both tend to infinity as x grows without bound, but their difference if x, gx, equals sine, one tends to a finite number. However, for other pairs of functions tending to infinity, their difference might tend to 0, another infinity, or fail to approach any limit at all. This indeterminacy exemplifies the infinity subtraction collapse in practical mathematics. Beyond mathematics, the paradox touches philosophy and physics. Philosophers have long pondered the nature of the infinite, questioning whether the universe is infinite in space or time. If the universe is infinite, can we meaningfully subtract one infinite region of space from another? What does that imply for cosmology and our understanding of existence? Similarly, in physics, theories involving infinite quantities often require careful handling to avoid nonsensical results. The idea that subtracting the infinite might lead to uncertainty warns us that some questions may resist definitive answers. The infinity subtraction collapse also reveals the limitations of human cognition. Our brains evolved to understand finite, tangible quantities and linear cause and effect. Infinity stretches these concepts to the breaking point, producing paradoxes that force us to reconsider assumptions about numbers, size, and operations. The paradox demands humility, reminding us that not all problems yield clear-cut answers, especially when dealing with the infinite. Ultimately, the infinity subtraction collapse is more than a mathematical curiosity. It is a profound exploration of the boundaries of knowledge and logic. It challenges our desire for certainty and compels us to embrace complexity and ambiguity. When infinity minus infinity can be 0, another infinity, or undefined, certainty becomes elusive, and understanding requires openness to multiple perspectives. In embracing this paradox, we learn to navigate the infinite with both wonder and caution. We recognize that some mysteries remain beyond resolution, inviting continuous inquiry rather than final answers. The infinity subtraction collapse thus stands as a testament to the beautiful, perplexing nature of infinity, a concept that forever expands our minds, pushing the limits of reason and imagination. The line segment reversal. Imagine a simple line segment, 2 points connected by a straight path. At first glance, it seems straightforward. Start here, end there, measure the distance, and you have length. But dive deeper into this seemingly simple concept, and you enter a world where what we think we know about space, distance, and continuity unravels into a profound mystery. This is the paradox of the line segment reversal, a concept that challenges our fundamental understanding of measurement and reality. Between any 2 points on a line, there are infinitely many others. Imagine 2 dots on a page. No matter how close they are, you can always find another point between them. And then another between those, endlessly. This infinite density is the backbone of the continuum. The idea that space is not made of discrete chunks, but is a smooth, unbroken whole. It feels intuitive, yet it defies common sense, because it suggests you can never truly isolate 2 points without an infinite cascade of points in between. Now, stretch those points too far apart. Imagine trying to measure the distance between 2 stars or galaxies millions of light years away. Suddenly, length becomes less about the straightforward path and more about the space-time fabric, warped and curved by gravity. The concept of length becomes elusive. How do you define a straight line across the universe when the fabric itself bends and twists? In such cosmic scales, distance is no longer absolute but relative, dependent on the observer's frame of reference. What is length, really? Is it just the measurement we take with rulers and tape measures in our everyday life? Or is it a deeper, more complex concept that blends geometry, physics, and philosophy? In mathematics, a line segment's length is a precise number, calculated from coordinates. But in physics, particularly in Einstein's theory of relativity, length can contract and expand depending on speed and gravity. The fixed line of our intuition gives way to a dynamic, flexible reality. This paradox also resonates in quantum physics, where at incredibly small scales, space might not be continuous at all. Some theories propose space is quantized, made up of discrete, smallest possible units. If so, then between those smallest points there is no infinite others. This would upend the classical idea of the line segment as an infinite continuum. The very nature of length at the quantum scale becomes mysterious and uncertain. In everyday life, we take length for granted. We measure a table, walk a path, or drive a distance, all relying on the assumption that length is fixed and meaningful. But the line segment reversal invites us to see beyond the surface. It teaches that length is not just a number, but a concept bound by context, scale, and perspective. This idea challenges us philosophically. How do we truly know the distance between 2 things? Is distance an inherent property of space, or is it a construct of our minds, shaped by perception and measurement tools? Ancient philosophers like Zeno of Elea wrestled with related paradoxes, like the famous Achilles and the tortoise, which explore how infinite subdivisions challenge our understanding of motion and distance. Mathematicians formalize this with the concept of limits and continuity, showing how infinite points can sum to a finite length. This reconciles the infinite divisibility of the line with our experience of measurable distances. Yet, the deeper question remains: does the line exist independently of our measurements, or is it inseparable from how we conceptualize space? Artists and architects, too, play with this idea. By manipulating perspective and scale, they create illusions that bend perceived length, showing how subjective our sense of distance can be. A hallway might appear endless or compressed, reminding us that length is also psychological and sensory. The line segment reversal is not just a mathematical curiosity. It touches the core of how we understand reality. It bridges the infinite and the finite, the abstract and the tangible. It forces us to question what we consider basic truths and invites wonder at the complexity lurking beneath simple concepts. In embracing this paradox, we grow in humility. We recognize that even the most fundamental notions, like the distance between 2 points, can be elusive and fluid. This awareness opens pathways to new scientific inquiries, philosophical reflections, and creative explorations. So next time you see a simple line drawn between 2 points, pause and reflect. Between those 2 points lies infinity, and beyond them, a universe where length bends, contracts, and transforms. The question, what is length really, is an invitation to journey deeper into the nature of existence itself. The countable, uncountable trap. Some infinities can be counted, others cannot. But between any 2 real numbers lie infinite decimals. Infinitely uncountable, This paradox lies at the heart of understanding the very nature of infinity, a concept that has fascinated, baffled, and mystified mathematicians and philosophers for centuries. The countable-uncountable trap reveals how infinity is not a single, uniform idea, but a spectrum of magnitudes that challenge our intuition and stretch the limits of human comprehension. To begin, infinity is often imagined as an endless expanse, a never-ending journey with no destination. We might picture the infinite as simply bigger and bigger, like counting natural numbers, 1, 2, 3, and so forth, forever. This is what mathematicians call a countable infinity. Even though it never ends, you can list these numbers one after the other, matching each to a distinct position in the list. This kind of infinity, while vast, is somewhat manageable because it aligns with the concept of counting. But then we encounter a profoundly deeper mystery. Between any two real numbers, say 1 and 2, lie infinitely many numbers. Not just infinitely many, but infinitely many decimals. Numbers like 1.1, 1.0, 1, 1.0, 1, and so on, stretching on forever with endless precision. These numbers cannot be put into a neat list or counted because their infinity is of a fundamentally different kind. This is called an uncountable infinity. The idea of uncountable infinity was rigorously demonstrated by the mathematician Georg Cantor in the late 19th century. Using his famous diagonal argument, Cantor showed that no matter how you attempt to list all the numbers between 0 and 1, there will always be numbers missing from the list. This proves that the infinity of real numbers between any 2 points is strictly larger than the infinity of natural numbers. In other words, some infinities are bigger than other infinities. This revelation is both thrilling and unsettling. It tells us that infinity is not just never-ending, but has layers of complexity and scale. The infinity of whole numbers is just one kind, a smaller infinity. The infinity of real numbers, with all their infinite decimal expansions, is a larger infinity. And between these lie other infinities, each with its own properties and challenges. To grasp why uncountable infinity defies listing, imagine trying to write down every number between 0 and 1. No matter how many you list, Cantor's diagonal argument constructs a new number that differs from every number in your list by at least one digit, proving your list was incomplete. This process goes on indefinitely, confirming that the set of real numbers is uncountable. The implications of this are vast. In mathematics, it means the continuum of real numbers forms a richer, more intricate structure than the discrete sequence of natural numbers. In philosophy, it challenges how we conceive of quantity, measure, and even reality itself. The concept that there are different sizes of infinity shakes the foundation of how we think about the infinite and the finite. Beyond theory, these ideas influence computer science and logic. Computers operate on discrete data, countable sets, but the continuous world they model, the real numbers, analog signals, probabilities, falls into the uncountable domain. This gap between the countable and uncountable informs the limits of computation and representation. The countable-uncountable trap is also a metaphor for human understanding. Some concepts, like natural numbers, fit neatly into our intuition and mental frameworks. Others, like the uncountable infinity of real numbers, resist simple comprehension, forcing us to expand our minds beyond everyday experience. Even in art and literature, the idea of infinite complexity hidden within seeming simplicity resonates deeply. The fractal patterns in nature, with endless detail at every scale, echo the uncountable infinity of numbers. Structures infinitely rich, yet bounded within finite spaces. This trap reminds us that not all infinities are created equal. The very fabric of mathematics, and perhaps reality, is woven with layers of infinite magnitudes, each challenging the limits of logic and imagination. Some infinities can be counted, listed, and grasped. Others remain vast oceans of possibility beyond enumeration. In the end, the countable-uncountable trap invites us to marvel at the subtlety of infinity. It compels us to accept that even in the infinite, there are hierarchies, distinctions, and mysteries. Infinity is not a simple concept, but a gateway to deeper understanding, one that stretches the mind and enriches the soul. So, next time you think of infinity, remember, some infinities you can count, but others stretch beyond counting, filling every space between with endless wonder. The Banach Tarski Nightmare. The Banach-Tarski nightmare is one of the most unsettling and mind-bending results in modern mathematics. It states that a solid sphere can be cut into a finite number of pieces, specifically 5, and these pieces can then be reassembled without any stretching or distortion into 2 identical copies of the original sphere. This idea feels like pure fantasy. It suggests that math can clone matter, creating perfect duplicates from nothing. Yet, this defies everything we understand about physical reality. How can this be possible? What does it mean? And why is it called a nightmare? To grasp this, we need to dive into the heart of set theory and geometric paradoxes. The Banach-Tarski paradox arises from the world of abstract mathematics, relying heavily on the axiom of choice, a foundational principle that allows for selecting elements from an infinite number of sets simultaneously. Using this axiom, mathematicians showed that certain sets in three-dimensional space can be decomposed and rearranged in ways that seem impossible in the physical world. The paradox says that you can take a solid ball, break it into a finite number of non-measurable sets. These pieces are not like ordinary shapes or fragments. They are highly complex, infinitely scattered, and so bizarre that they cannot be assigned a volume in the conventional sense. Because of this, when you reassemble them, you can create 2 balls identical in size to the original. It appears as if matter duplicates itself, violating conservation laws. At first glance, this feels like an invitation to magical duplication or infinite resources. Imagine a world where you could split your possessions into pieces and rearrange them to double everything you own. But reality refuses this logic. Physical objects are made of atoms, obey laws of physics, and cannot be broken down into these infinitely complex, non-measurable sets. The Banach-Tarski paradox exists purely in the realm of mathematical abstraction, divorced from physical constraints. This paradox challenges our very notions of volume, measure, and reality. It exposes the limits of our intuition when confronted with infinite sets and abstract reasoning. In everyday life, volume is additive. You cut something in pieces, sum their volumes, and get the total. The paradox shows this isn't always true in the abstract mathematical universe, where additivity of volume breaks down under certain conditions. The implications of the Banach-Tarski paradox reach deep into mathematics and philosophy. It questions what it means for a property like volume to be well defined and how our mathematical tools relate to the real world. It forces us to confront the tension between elegant mathematical theories and the messy, constrained reality we live in. Some have feared that this paradox threatens the foundation of measure theory, or physics, but it does not. Physicists rely on models grounded in measurable quantities, where the paradox does not apply. The pieces in the paradox are not physical fragments, but abstract constructions that cannot exist materially. Still, the Banach-Tarski nightmare haunts mathematicians and philosophers alike. It's a vivid reminder that mathematics is not just a mirror of reality, but a landscape of ideas that can outstrip and contradict physical intuition. It challenges us to be humble about the limits of human understanding. The paradox also has analogies in other areas, like quantum physics and information theory, where our classical concepts of locality, duplication, and conservation are challenged. While we cannot duplicate matter as the paradox suggests, the notion of information cloning or state replication underlies many cutting-edge scientific debates. In the end, the Banach-Tarski nightmare is both a marvel and a warning. It marvels in the power of abstract logic to reveal astonishing truths about infinite sets and structures. It warns us about assuming that mathematical truths always translate directly into the physical world. To embrace this paradox is to embrace complexity and uncertainty. It's an invitation to explore how deep mathematical ideas shape, but do not dictate our understanding of reality. And it reminds us that reality is sometimes stranger and more constrained than the elegant theorems we construct. This paradox fascinates because it stretches the boundaries of logic and imagination. It forces us to ask, what is real? What does it mean to measure or to duplicate? And ultimately, it shows that even the most fundamental concepts, like volume and matter, are not as absolute as they seem when viewed through the lens of infinity. The Banach-Tarski nightmare will remain a profound and unsettling puzzle at the crossroads of math, philosophy, and physics. It reminds us that some truths lie beyond intuition, waiting to be understood in the language of pure abstraction. The angle, without a vertex, imagine an angle, a sharp corner where two lines meet at a point. That point, the vertex, is a location without size, without area, without mass. It's nothing more than a position in space. If you look at that single vertex, it's essentially zero, a concept that defies physical substance, a point without dimension. Yet, when you combine countless such points, corners, and edges, something remarkable happens. Shapes emerge, volumes take form, matter gains presence, and meaning unfolds. This is the paradox of the angle without a vertex. From nothingness arises something. The zero-dimensional point itself holds no mass or volume, no area to touch or see. Yet, it is the foundational origin, the beginning, of everything that exists in space. To grasp this, we must first understand the nature of zero and points in geometry and philosophy. A point represents an exact location. It has position, but no size. The vertex of an angle is just such a point. On its own, it's intangible and invisible, yet it anchors lines, angles, and ultimately, shapes. Imagine drawing a single dot on paper. The dot represents a point but physically has some size because of the pen's ink. However, in pure mathematics, the point is infinitely small, dimensionless. It marks a place without taking up space. When two lines meet at such a point, they form an angle. The angle itself, measured in degrees or radians, has a measure but no area if taken in isolation. The corner is a boundary, a meeting place, not a filled space. Now, consider assembling many of these corners and edges. A triangle, the simplest polygon, is formed by connecting 3 points with 3 edges. The triangle encloses area, a two-dimensional space. Add more points and edges and you get polygons, polyhedra, and eventually 3-dimensional solids. Suddenly, from dimensionless points and lines, we build mass and volume. This concept transcends geometry into physics and cosmology. The fabric of reality, at the smallest scales, can be thought of as constructed from fundamental points or particles, entities without dimension in classical terms. The very essence of space-time may arise from relationships among these elemental points. Philosophically, this raises profound questions. Is zero, the absence of quantity, the true origin of all existence? Can the void or the empty point be the seed from which complexity and meaning spring? It challenges our intuition that creation begins with something tangible. Historically, thinkers from Euclid to modern mathematicians have explored points and dimensions as abstract concepts. In modern physics, quantum theory suggests that at the Planck scale, space and time themselves are quantized, discrete points forming the scaffold of reality. In art and architecture, the point and angle are foundational. A single vertex determines form and structure. The Gothic cathedral's sharp angles and spires arise from geometric principles starting with simple points. The beauty and complexity emerge from the assembly of countless nothingnesses. On a metaphorical level, the angle without a vertex invites reflection on existence and identity. How can something arise from seemingly nothing? How do small, invisible points connect to create meaning, purpose, and life? It is a reminder that the foundations of reality and understanding often lie in what appears empty or void. This idea also resonates with experiences of consciousness. Our sense of self may feel like a singular point, intangible and elusive, yet from that emerges the vast landscape of thoughts, feelings, and perceptions. The angle without a vertex is a symbol of paradox. Zero is origin, absence is source, emptiness is potential. It urges us to reconsider how we define existence, presence, and meaning. As you ponder this, consider the profound power hidden in the smallest, most overlooked elements of reality. The vertex without area is not a void, but a seed. It is not absence, but possibility. From that point, the universe unfolds. So, is zero the origin of everything? In the quiet, dimensionless point where lines meet, perhaps lies the answer. The stillness before creation, the space from which all shapes, masses, and meanings emerge. The volume of nothing, a shape with infinite surface area and zero volume, is a paradox that defies our most basic intuitions about space, matter, and existence. It is a phenomenon that pushes the boundaries of geometry and challenges how we conceive the very notion of nothingness. How can something exist, occupy space, and be defined by a boundary so vast that its surface is infinite, yet enclose absolutely no volume inside? This enigma leads us on a deep exploration into the mysteries of space, the fabric of reality, and the elusive nature of emptiness. What truly lives inside nothingness? To begin, let's unpack the mathematical context of this paradox. In classical geometry, shapes are defined by their boundaries, lines, surfaces that enclose space. A sphere has a surface that wraps around a volume. A cube's faces form a shell containing space inside. Typically, an increase in surface area correlates with an increase in volume. But fractal geometry, a branch of mathematics exploring infinitely complex patterns, turns this assumption on its head. One of the most famous fractal shapes is the Koch snowflake. Starting from an equilateral triangle, the Koch snowflake is created by repeatedly adding smaller triangles to each side, ad infinitum. With every iteration, the perimeter becomes more jagged and increases in length without bound. In fact, the snowflake's boundary length tends toward infinity. Yet, despite this infinite perimeter, the area enclosed by the snowflake remains finite, never exceeding a specific limit. This example alone unsettles our normal understanding. Infinite boundary, yet finite enclosed space. But mathematics goes even further. Researchers have constructed theoretical shapes that push this paradox to its extreme. Shapes with infinite surface area, but zero volume. These are bodies whose boundaries, when viewed at every scale, reveal an endless complexity. A surface so crinkled and folded it stretches without end, but the space inside shrinks down to nothing. How is this possible? The key lies in how fractals behave at different scales. Unlike smooth surfaces, fractal boundaries reveal detail no matter how closely you look, repeating their patterns endlessly. This infinite complexity inflates the surface measure, but because these folds become finer and finer, they fail to enclose measurable volume. It's as if the shape breathes existence into space without truly capturing it. This paradox does more than challenge geometry. It shakes the foundation of how we understand existence itself. Philosophers have long debated the nature of emptiness and nothingness. The notion that something can have a boundary, an edge or limit, yet contain no substance, forces us to reconsider what it means for space to be empty. In physics, this concept resonates with the study of the vacuum. Quantum physics reveals that the vacuum is not an empty void, but a seething field of energy and fluctuating particles appearing and disappearing in an eternal dance. While mathematically we may conceive a zero-volume shape with infinite boundary, the physical universe tells us emptiness may harbor structure and potential. Cosmologists speculate on the shape and size of the universe. Could the cosmos itself have fractal-like boundaries or structures invisible to current instruments? Could infinite boundaries encapsulate zero net volume on cosmic scales? These are open questions, but the mathematical paradox sparks profound curiosity about the hidden fabric of reality. Even in art and symbolism, the volume of nothing represents the tension between presence and absence. It is the silent canvas, the negative space that gives form meaning. The paradox invites us to reflect on the power of emptiness, not as mere void, but as a space pregnant with possibility and mystery. What lives inside nothingness? Is it truly empty, or does it hold the seeds of creation? Perhaps inside nothingness dwells potential, an infinite possibility that defies containment and definition. The paradox of infinite surface area with zero volume is a metaphor for existence itself. Complex, paradoxical, and beyond full comprehension. In confronting this mystery, we face the limits of human knowledge and perception. The infinite boundary with no volume is a riddle that reminds us humility in the face of the unknown. It calls us to explore with open minds, to accept ambiguity, and to embrace the paradox as part of the journey toward deeper understanding. Ultimately, the volume of nothing is not just a mathematical curiosity, it is a profound invitation to question reality, to seek beyond appearances, and to marvel at the infinite complexity woven into the very fabric of space and emptiness. It challenges us to see that nothingness is not mere absence, but a living, breathing concept where the boundaries of existence and void intertwine. And so, as we ponder what lives inside nothingness, we come to realize that the answer may not be a concrete thing at all. Instead, it is the space of endless possibility, the canvas upon which all things are drawn, and the infinite mystery that lies at the heart of everything. The infinite hotel paradox. Imagine a hotel with infinitely many rooms. Every single one is occupied, completely full, no vacancies. Yet, somehow this hotel can still welcome new guests endlessly. This is Hilbert's infinite hotel paradox, a mind-bending thought experiment that challenges our understanding of infinity, accommodation, and the very nature of numbers. At first, the idea seems impossible. If all rooms are occupied, how can there be space for more guests? In a finite hotel, when full, you turn people away. But in Hilbert's hotel, the rules of infinity rewrite the game. Because the hotel has infinite rooms, it can rearrange its occupants in ways that create space out of what seems like nothing. Here's how it works. When a new guest arrives, the manager asks every current guest to move from room n to room n+1. The guest in room 1 moves to room 2 moves to room 3, and so on, pushing everyone one room forward. Suddenly, room 1 becomes free for the newcomer. Despite being full, the hotel can accommodate this additional guest without evicting anyone. This idea stretches even further. What if an infinite number of new guests arrive at once? The hotel manager can ask the guest in room 1 to move to room 2 to room 4, room 3 to room 6, effectively doubling every occupant's room number. This move frees all the odd-numbered rooms, infinitely many of them, ready to welcome the infinite new arrivals. Hilbert's hotel shows how infinite sets defy our finite intuitions. Infinity isn't just a large number. It behaves in ways that seem paradoxical and counterintuitive. The hotel never runs out of rooms because the set of natural numbers, representing room numbers, can be mapped onto a proper subset of itself, a fascinating property of infinite sets known as being countably infinite. Mathematically, this concept introduces the idea that some infinities can be put into one-to-one correspondence with proper subsets of themselves, something impossible for finite sets. This challenges how we think about size and quantity, revealing the complex and rich structure within infinity. Beyond math, the paradox invites philosophical reflection. It questions how we conceive space, capacity, and possibility. It hints at the limits of human intuition when grappling with concepts beyond everyday experience. In physics and cosmology, infinity plays a crucial role too. The universe's size, the concept of infinite parallel worlds, or infinite points in space-time echo the themes of Hilbert's hotel, showing how infinity isn't just abstract, but woven into the fabric of reality. Hilbert's infinite hotel reminds us that infinity has its own logic, one that stretches, bends, and reshapes our understanding. It teaches us humility in the face of the infinite, and encourages curiosity about the vastness beyond our finite world. So, next time you think about a hotel being full, remember Hilbert's paradox. Infinity never fills up. It always finds room for one more, and one more after that, endlessly. The zero division ghost. Divide 1 by 0 and you summon a ghost, a phantom concept that haunts mathematics and defies all logic. What is 1 divided by 0? Undefined, infinite, forbidden. This is the zero division ghost, a paradox that reveals the fragile boundaries of our number system and exposes the limits of mathematical certainty. Attempting to divide something by nothing is not just an error, it is an act that shatters the number line, rupturing the foundations of arithmetic itself. At first glance, division seems straightforward, splitting a quantity into equal parts. Divide 6 by 3 and you get 2. Divide 10 by 5 and you get 2 again. But what happens when the divisor is 0? How many times does 0 fit into 1? The question breaks down because 0 times any number is always 0. There's no number that, multiplied by 0, will give you 1. So the operation becomes impossible to define within our usual arithmetic rules. Mathematicians declare division by 0, undefined, but the zero division ghost is more than a simple rule. It's a warning sign of deeper instability. If we were to accept that 1 divided by 0 equals some number, strange contradictions would follow. For instance, if 1 divided 0 equals x, then multiplying both sides by 0 would imply 1 equals x times 0, which equals 0, an absurdity. This paradox shows that dividing by 0 doesn't just fail, it undermines the logical consistency of mathematics. Historically, the concept of 0 itself was revolutionary, a symbol for nothingness that allowed the development of place value and modern arithmetic. But 0's properties introduce delicate challenges. Division by 0 is like touching the edge of a cliff where mathematics breaks down, revealing gaps in our understanding. The zero division ghost also appears in calculus and physics. In limits, expressions approach division by 0, often leading to infinite values or undefined behaviors. For example, The function 1x grows without bound as x approaches 0 from the positive side, hinting at infinity but never actually reaching division by 0. These approaching behaviors allow mathematicians to work around the ghost, capturing tendencies without invoking the forbidden operation directly. Yet, the ghost persists in symbolic form, reminding us that some operations are inherently unstable. In computer programming, division by 0 often causes errors or crashes, symbolizing the real-world consequences of confronting this mathematical paradox. The zero division ghost is not just a technical quirk, but a profound symbol of limits and boundaries. It shows that our most trusted systems have edges where definitions fail and logic falters. It challenges us to respect these boundaries, even as we seek to understand what lies beyond. Philosophically, it raises questions about nothingness, infinity, and the meaning of division itself. Dividing by 0 is like trying to measure the immeasurable or to split the indivisible. It evokes the tension between the finite and the infinite, the known and the unknowable. In the end, the zero division ghost teaches humility in the face of mathematical complexity. It warns that some concepts, when pushed too far, reveal instability that demands new frameworks or perspectives. It inspires mathematicians to develop richer theories, like projective geometry or extended number systems, that can handle these paradoxes in novel ways. So, next time you encounter division by 0, remember, you're summoning a ghost, a concept so unstable it shatters the number line and beckons us toward deeper understanding of infinity, nothingness, and the limits of logic. The hidden number fallacy. You can prove 2 equals 0 with just a few symbolic substitutions until you realize the laws you trusted were silently broken mid-proof. This is the hidden number fallacy, a fascinating and unsettling phenomenon in mathematics where flawed reasoning or subtle missteps give rise to seemingly absurd conclusions. It exposes how easily our confidence in logic can be undermined when hidden assumptions or forbidden operations sneak into a proof. At its core, mathematics is built on rigorous rules and logical steps. Every equation, every manipulation follows strict laws to ensure that conclusions are true and reliable. But sometimes, a proof will lead you to an impossible statement, like 2 equals sign 0 or 1 equals sign 2. These proofs are often crafted with a mix of true statements and deceptive moves that violate fundamental principles, usually without making the violation obvious at first glance. Take the classic example of proving 2 equals 0. The proof begins innocently enough. Algebraic expressions are rewritten, terms are factored, and equalities substituted. Each step looks legitimate. But somewhere in the process, a division by 0 occurs, or an invalid cancellation is made, breaking the rules silently. Since division by 0 is undefined, the logic collapses, making the proof invalid. Yet, to the casual observer, the argument appears airtight. This fallacy is a powerful lesson in mathematical rigor. It teaches us to be vigilant about the assumptions embedded in every step of a proof. The hidden fault, often a forbidden operation or an unstated condition, can invalidate the entire argument, no matter how convincing it seems. Beyond pure mathematics, the hidden number fallacy serves as a metaphor for errors in reasoning and argumentation everywhere. It shows how subtle logical breaches can lead to false conclusions, misleading beliefs, or even dangerous ideologies if left unchecked. In education, exposing students to such fallacies encourages critical thinking and a deeper understanding of the importance of rules. It reveals that mathematical proofs are not mere formalities, but delicate constructions that require careful attention. Philosophically, it reminds us that truth depends not only on outcomes, but on the integrity of the process. An apparently brilliant result is worthless if achieved through hidden cheating or rule-breaking. The hidden number fallacy also warns against the temptation to accept astonishing claims without scrutiny. Extraordinary conclusions demand extraordinary proof, and even then, we must question the foundations. In the end, this fallacy is a humbling reminder. Logic is only as strong as the laws we choose to uphold, and the care with which we apply them. When those laws are quietly violated, the entire structure of reason can crumble, revealing illusions disguised as certainty. Understanding this fallacy sharpens our minds, guards against deception, and deepens our appreciation for the precision and honesty required in mathematics and beyond. The paradox of density. Imagine a world built entirely out of numbers. every point, every step, every thought, is marked on a never-ending line stretching from negative infinity to infinity, an endless silent field where each number is a unique star. At first, the land seems simple. Every number can be counted, or so it feels, because we start with the rationals, the fractions. Numbers like 1/2, 5/7, 12/101. For every rational number, there is a numerator and a denominator, both whole numbers, both chosen and clear. You can, in principle, list them. If you're patient enough, you can count every rational number that has ever existed, or will ever exist. They are infinite, yes, but countable, like grains of rice in a bottomless sack. But now the paradox sharpens. Between any two rationals, say between 1/2 and 2/3, there's always another rational. You could take their average, or pick another fraction with a bigger denominator, and squeeze it in between. This is density. No matter how close you get, you can always get closer, and yet you never run out. But this density, paradoxically, isn't the full story. In the spaces between the rationales, something stranger lurks. Something so abundant, so wild, that it outnumbers the rationals in a way the mind cannot picture. Enter the irrationals, numbers like pi, 2, e, or the mysterious decimals that never end, never repeat, never fall into a pattern. Their existence explodes the idea of order. The rationals, with all their infinite march, are just pinpricks in a storm. The irrationals are uncountable. Their infinity is so much vaster that if you picked a random number from the number line, the chance of hitting a rationale is actually 0. That's right. The rationals are dense, but compared to the ocean of irrationals, they're invisible. If you zoom in on the number line, you will always find rationals, always. But the space is dominated by the unseeable, untouchable sea of irrationals. Let's see how strange this gets. Take two rational numbers, 1/3 and 1/2. We know there's a rational between them, say 2/5. But now, can you find an irrational between them? Of course. For example, take 1/3 plus 2 to 100, which lands between 1/3 and 1/2. That number will be irrational. And there are not just a few, but infinitely, uncountably many such irrationals. In fact, between any two rationals, no matter how close, the irrational numbers between them vastly outnumber the rationals, so much so that rationals seem almost absent. Now, look at it another way. Imagine you're constructing a line segment. At every step, you're allowed to pick either a rational or an irrational point to mark. If you restrict yourself to rationals, you're forever marching along points you could, in theory, name. You could make a list, first this fraction, then that. But if you open the door to the irrationals, you invite in a storm that cannot be organized. There's no list you could ever make, even in eternity, that would capture them all. They're everywhere. Between any two rationals, between any two irrationals, even between a rational and an irrational, there is always another irrational, always another unnameable number. Infinitely more than you can imagine. But here is where the paradox truly strikes. The rationals are both everywhere and nowhere. They are dense, which means they fill the number line so completely that, no matter where you stand, there is always a rational right next to you. Yet, taken as a whole, they are almost nothing compared to the uncountable infinity of the irrationals. The rationals form a skeleton, thin, fragile, endless. But the flesh, the substance, the life of the number line, is irrational. The paradox of density is that you can have an infinite set that is dense everywhere but so small compared to the uncountable that it is like dust in the air. Let's deepen the strangeness with a thought experiment. Imagine a hotel, infinite in size, with a room for every rational number. You could, in principle, name every guest, every room. Now imagine the hotel of the irrationals. There aren't enough names, not even in all the languages ever spoken, to assign to the guests. There is no way to line them up, no way to count them, even if you tried forever. But paradoxically, between every two rooms in the rational hotel, there is an infinity of irrational guests hiding in cracks, like ghosts, untouchable, never on the guest list. Why does this matter? In mathematics, it tears apart the idea that everything can be counted, listed, put in order. In physics, it means the world is full of values you cannot write down. Distances, times, probabilities, all hiding secret irrational depths. In philosophy, it attacks the concept of order itself. How can you have something so everywhere, so ever-present, that is still, in a sense, almost nothing compared to its neighbors. Let's put it in the language of paradox. Suppose you had a magical dartboard, a perfect one, stretching across all real numbers from 0 to 1. You throw a dart, blindfolded. What are the chances you hit a rational? Mathematically, the answer is 0. But if you ask, are the rationales there? The answer is yes, everywhere. In fact, you could spend an eternity just picking rationals and never run out. Yet, in the grand scheme, your chances of hitting one are 0. Infinity can be dense but still vanish when faced with a larger infinity. Here's another way to feel the paradox. List all the rationales as decimals. Some terminate, some repeat. Now, make a number that is different in every decimal place from every number in your list. This new number must exist. It's not rational. It's something else. This is the heart of Cantor's famous diagonal argument. No matter how hard you try to capture all numbers in a net of rationals, there will always be escapees. Irrationals that cannot be named, cannot be counted, but are more real in a sense than the rationals themselves. So, when you walk along the number line, think about this. Every rational is a step you could take, a destination you can name. But the path itself, the infinite road beneath your feet, is made of irrationals, places you can never stand, numbers you can never write, but which hold up the entire world. The rationals are like notes in a silent symphony. They seem to fill the air, but it's the spaces between, the unseen, the untouchable, that truly carry the music. This is the paradox of density. The rationals are countable, dense, present at every turn, yet they're overwhelmed by the vast, chaotic infinity of the irrationals. Between any two rationals, no matter how tightly you squeeze them, lies an irrational. And between any two irrationals, more irrationals again. In this world, order dissolves, certainty dissolves. What looks structured and familiar is swallowed by the uncountable, and the more you look, the more the illusion of order slips away. So, next time you write a simple fraction or try to measure a distance, remember, you are treading on a line so thick with mystery, so rich with numbers you can never know, that your chosen, countable points are just tiny beacons in an infinite, swirling sea. And in that sea, the rules you trusted begin to blur. The closer you look, the less you understand. Until finally, all that remains is the strange, beautiful paradox that density in mathematics and in life is never what it seems. The frozen motion problem. Imagine this. You stand at the edge of a room, eyes fixed on a closed door at the other end. It's a simple task. Walk forward and reach the door. You take your first step, feeling the familiar motion of your body carrying you across the floor. Nothing feels strange. You're not thinking about mathematics or philosophy or the impossibility of what you're doing. You're simply moving through space, trusting that as long as you walk, you'll arrive. But beneath this ordinary act, an ancient thought experiment is quietly unraveling the certainty of motion. Zeno of Elea, a philosopher from over 2,000 years ago, posed a paradox so sharp that it slices through the fabric of logic and reality itself. He argued that before you can reach the door, you must first reach the halfway point. And before you reach the halfway point, you must reach the quarter mark. Before that, the 8th, the 16th, the 32nd. The process never ends. Every step contains another step, another fraction, another midpoint waiting to be crossed. Infinity, lurking in the dust beneath your feet. According to Zeno's reasoning, you must cross an infinite number of points before reaching any destination. Even the simplest, most mundane goal, like touching a door at the end of a hallway. So, if an infinite task can never be completed, how is it possible that you ever arrive at your goal? Why aren't you, right now, frozen mid-step, caught forever in an endless process, unable to finish even the smallest journey? This isn't just a brain game. Zeno's paradox is a genuine wound in the fabric of logic, a challenge to everything we believe about movement, time, and even reality. For thousands of years, philosophers and mathematicians grappled with this question, haunted by the suspicion that motion itself might be an illusion, a trick of the mind, as impossible as a never-ending staircase. Imagine a world where every time you tried to reach for something, the goal would split itself in half, then half again, receding forever, always a little closer, but never quite within reach. This is the frozen motion problem. At its heart lies the terrifying possibility that movement as we perceive it is fundamentally impossible. To understand why, consider what infinity truly means, not as a distant cosmic number, but as something hiding in the most basic action. You stretch out your hand to grasp a glass of water. Between your hand and the glass lies an infinite number of invisible boundaries, each requiring a crossing, each subdividing the remaining distance. It's as if reality itself is composed not of continuous flows, but of countless still frames, like a film reel that never quite completes the scene. This is not just abstract philosophy, it shapes how we understand the world. The paradox challenges our sense of time and space. If every journey is built of infinite steps, then how can any process ever finish? Why isn't the universe stuck, every atom frozen in a cosmic gridlock? Yet, we do reach the door. The arrow does hit its target. Achilles does overtake the tortoise. Is Zeno wrong, or is our experience an illusion? For centuries, no one could answer this with confidence. The ancient Greeks were haunted by the specter of infinity, something so large and all-consuming, it defied the very idea of completing anything. Even as science advanced, the paradox persisted, casting its long shadow over calculus, mathematics, and physics. It wasn't until the 17th century that mathematicians like Newton and Leibniz began to wrestle infinity into submission with the invention of calculus. Their breakthrough, the concept of the limit. Instead of asking whether you can ever complete an infinite series of steps, calculus asks what happens as you get closer and closer to your destination. If the sum of all those infinitely small steps adds up to a finite distance, then motion is possible. But does this really solve the problem, or just brush it aside with new vocabulary? After all, the infinity is still there, lurking under every footstep, every heartbeat. When you walk, your brain and body are navigating an unending sequence of tasks, an infinite complexity compressed into a single gesture. The paradox is resolved mathematically, but the philosophical shockwave remains. Think about digital video, where every moment is made of still images, frames that flicker past at 24 or 60 times per second. If you slow it down enough, you see each frozen instant. Yet, when the film plays at full speed, your mind stitches the images together, creating the illusion of continuous movement. Could reality itself be made this way? A flickering sequence of static moments, woven together by the mind into the tapestry of time? Is motion an illusion we've agreed to believe simply because it's convenient? Let's go deeper. In quantum physics, the smallest scales of reality are not smooth, but grainy, pixelated at the Planck length, where space and time become granular. Some physicists wonder, is the universe itself a kind of cosmic film strip? And what we call motion is just our consciousness jumping from one frame to the next? If so, Zeno's paradox isn't just a puzzle, it's a clue to the underlying structure of the cosmos. Yet, none of this erases the feeling of movement. No matter how many times you split the distance, your experience is that of flowing forward, not stalling forever. You reach the door. The runner overtakes the tortoise. The arrow flies true. Motion happens, even if logic insists that it shouldn't. Is this a testament to the triumph of experience over theory, or are we simply blind to the mechanisms that let reality cheat infinity? The frozen motion problem is not just about mathematics or philosophy. It's about trust. Every time you take a step, you place your faith in the world's ability to deliver you from one place to another, despite the lurking infinity beneath your feet. You are, in a sense, defying Zeno with every action. You are a rebel against the tyranny of the infinite. So, next time you walk across a room, pause for a moment. Feel the strangeness in each stride. Remember that the simple act of moving forward contains a problem so deep and mysterious that it once paralyzed the greatest minds in history. And know that even now, as we explain and rationalize and calculate, the infinite still whispers beneath the surface of every journey. Motion is possible, but its possibility remains a miracle, a daily defiance of the endless divisions that lie hidden between you and the door. The rope around Earth paradox. Imagine standing on the edge of the ocean at midnight. The world is quiet. You stretch a single, perfectly tight rope around the entire equator of the Earth, an unimaginably long rope, pulled snug so it hugs every inch of land and sea, every mountain and valley. The length of this rope is, for all practical purposes, a number so massive the mind flinches. Earth's circumference at the equator is about 24,901 miles, or roughly 131,480,184 feet. Now, imagine someone gives you an extra 6 feet and a few inches, precisely 6.28 feet. They say, add this to your rope, make it longer by just this tiny amount. You tie the rope back together. The question arises, how high above Earth's surface will the rope now float if you lift it so it's evenly suspended everywhere, no longer pressed against the ground? The answer, and the paradox, is that the rope floats exactly 1 foot above the ground, all the way around the world. Not just at one point, not only where the continents are flat or the oceans are calm, but every inch of the way. A single extra foot for every mile? No, just 1 foot of height, globally, by adding what feels like a pitifully small amount of rope. This feels impossible. It feels like reality is bending, or that mathematics is playing a trick, but it isn't. The logic is pristine, and this is one of those moments where scale and our human intuition shatter like thin glass. Let's break this open. You might think, surely if I want to raise the rope even an inch above Earth everywhere, I'd need millions of feet of extra rope, something enormous. But what's really going on is far deeper. The core of the paradox lies in the relationship between the circumference of a circle and its radius. The formula, known by almost every student, circumference equals sine 2x pix radius. When you add more length to the circumference, you're effectively increasing the radius of the circle. The key is, for any circle, no matter how large, if you add a fixed length to the circumference, the increase in radius is always that extra length divided by 2p. It doesn't matter if you're talking about a basketball, a hula hoop, or the entire Earth. So, if you add 2p feet of rope, you increase the radius by 1 foot. The scale of the circle is irrelevant. Earth could be a planet 10 times the size, or just a pebble. The result is the same. The rope floats a uniform foot above the surface. It feels like you're cheating. How can something as small as 6.28 feet shift an entire planet's boundary rope an entire foot above ground? This is the part that collides violently with our common sense, which is tuned for kitchens and living rooms, not planetary geometry. We think linearly, not exponentially. Our minds are trained for small things. This paradox emerges as a slap across the face, a moment where you realize your everyday reasoning is powerless. The lesson hits you. The world is not always what it appears to be at scale. Try to picture it. You're holding this rope, standing at the edge of a beach, watching it float exactly a foot above the sand, stretching out of sight into the horizon. You know that on the far side of the planet, that same rope is floating a foot above a jungle canopy, or over silent Arctic ice. The extra rope you hold is so short you could carry it over your shoulder. And yet, this minuscule addition is enough to lift the entire rope above the surface of a world. It's absurd. It's mathematically perfect. To bring it even closer, let's shrink the scenario. Imagine wrapping a piece of string around a tennis ball. You measure, tie it tight, then add just a little more. Enough so, according to the formula, the string floats exactly a foot above the tennis ball, suspended by invisible spacers. Of course, a foot is far larger than a tennis ball, so in practice the string would be orbiting the ball from a huge distance. But the mathematics holds. The increase in radius is always that added length, divided by 2p. Let's flip it. What if you wanted the rope to float an inch above the surface of the Earth, not a foot? You'd only need to add about 2p inches, which is just over half a foot, barely the length of your forearm. The mind reels. How is this possible? Because as you scale up, the relationship between circumference and radius means each unit of rope has to go a long way, but every tiny extension gets distributed perfectly around the circle, lifting it everywhere by the same amount. The principle cares nothing for scale. Now, imagine what this means on other worlds. What if, instead of the Earth, you wrapped a rope around the sun, or even a black hole? The rules don't change. The paradox remains. Add a few extra feet and you're lifting that rope far above unimaginable surfaces, the logic gliding over distances that dwarf human existence. Let's explore why our minds reject this so violently. In day-to-day life, we're used to proportionality. If you add a small bit to a small thing, the effect is small. Add a small bit to a huge thing, the effect should be negligible, right? Yet, in this scenario, the scale seems to vanish. You're not adding a little bit to get a little change. You're adding a tiny bit and getting an everywhere change, no matter how big the original object is. This undermines our intuition, exposes the cracks in our thinking, and reveals the subtle terror of abstraction. What's so intoxicating about this paradox is the silent power of scale. Our senses are limited. We think the vastness of the earth swallows all difference. We assume that anything we add to something so massive will be diluted, made irrelevant by size. But mathematics is ruthless. It slices away our expectations and shows that the world of circles, ropes, and spheres follows a deeper code. No matter how large the circle, no matter what material the rope is made from, if you add 2p feet, you gain 1 foot of height. The rules do not care about your imagination, your expectations, or your sense of proportion. Now, let's look at an analogy. Imagine you build a fence around your garden and then you add a single inch to its length. The fence rises a fraction of an inch above the grass, barely noticeable. But wrap a fence around a continent, and if you add just enough length, it rises the same distance everywhere. The more massive the circle, the more impossible it seems. But it is always true. The ratio of circumference to radius is fixed by pi, and the consequences play out with eerie consistency. This is why the rope around Earth paradox is more than a mathematical party trick. It's a lens into the chasm between intuition and reality, a moment that leaves you suspicious of your senses and newly respectful of the abstract. You start to wonder, what other assumptions do you make about scale, about size, about what it takes to change the world? How many other laws are lurking, invisible, just beneath the skin of the obvious? Think about engineering, or city planning, or even astronomy. In each field, the tension between scale and proportion lurks. Bridges collapse, orbits drift, systems fail, not always because of mistakes in measurement, but because our brains are ill-equipped to handle scale. When you think you understand how things work, moments like this force you to realize that reality doesn't care what you think is obvious. Mathematics rules, and it does not consult your gut feeling. In the end, the rope around Earth paradox is a haunting reminder of our limitations. It's an invitation to humility, a whisper from the edge of reason that says, the universe is stranger than you can know, and scale bends in silence. The next time you see a rope or a circle or anything vast and unyielding, remember that a little change, if you know the right place to put it, can alter everything. The boundaries of the world can be lifted by the length of a single step, and sometimes the smallest additions carry the most cosmic consequences. So, if you ever find yourself doubting the power of mathematics, or feeling that the world is simply too big for small things to matter, remember this. One turn of the rope, one tiny extension, can raise the edge of reality itself, floating silently and impossibly above the surface of the world. The infinite choice trap. Imagine a blank line stretching perfectly from 0 to 1. This is not just a line on paper, it's a portal, a gateway to the uncountable, an infinite ocean hiding within a finite space. Now, imagine I ask you to pick a number, any number between 0 and 1. Sounds simple, right? Maybe you're tempted to say 0.5 comma right in the middle, or 0.25 comma, a neat quarter. But these numbers, the ones our minds leap to first, are merely islands, tiny, familiar spots poking out from a sea so vast that it's almost impossible to imagine. Here's where the paradox sharpens its blade. Mathematicians tell us that there are uncountably infinite numbers between 0 and 1, not just a lot, not just billions or trillions, but so many that even if you tried to count them one every nanosecond since the dawn of time, you'd never even approach a fraction of infinity. Every decimal expansion you can dream up, no matter how random or intricate, belongs somewhere on that line. Every random sequence of digits, every number you can name, and every number you could never name, all tucked between 0 and 1. But the truly wild part isn't just how many numbers there are. It's what probability theory says about the act of choosing one. Let's play a game. Suppose you close your eyes, spin a mystical wheel of infinite precision, and let fate pick a number between 0 and 1. Here's the trap. The probability that you pick exactly any specific number is mathematically 0. Not just unlikely, not just rare, 0. It doesn't matter which number you name, 0.1, 0.9999, 0.3333 repeating, even some strange number like 0.483927193. The chance of landing on that exact value in this infinite expanse is 0. Pause for a second and let that hit you. In our finite world, zero probability usually means impossible. But here, impossibility doesn't mean it can't happen. If you must pick, you must land somewhere. You always do. And yet, the chance of picking any particular place is still zero. This is the infinite choice trap. A place where logic seems to bend, where every outcome is possible and yet mathematically forbidden at the same time. So, how do we even begin to grasp this? Let's anchor ourselves with an analogy. Imagine an enormous library with infinite shelves, each shelf infinitely long, every single book containing a different decimal expansion between 0 and 1. You walk in and someone says, "Pick one book, any book at all." You walk along, eyes scanning the endless volumes, knowing that each book is unique, filled with a sequence of numbers that's never repeated anywhere else in the building. But here's the kicker. The probability of you choosing any particular book from this infinite library is 0. Yet you must pick. You cannot exit empty-handed. Still, you will never, by accident, select the book someone else had in mind. Now, stretch your imagination. Think of how we use numbers in daily life. Prices, scores, coordinates, probabilities, every one of them is a finite, rational, manageable entity. But these are mere shadows. The real numbers lurking between 0 and 1 are so numerous, so staggeringly vast, that most of them can never even be written down or described. In fact, almost all of them are what mathematicians call irrational. They can't be expressed as a neat ratio of two whole numbers, and their decimal expansions go on forever, never repeating, never ending, never settling into a pattern. Even more, most real numbers are actually transcendental, meaning they cannot even be roots of any polynomial equation with rational coefficients. Their existence is not just unnameable, it's fundamentally unknowable. Let's deepen the paradox. If you wrote a computer program to randomly select a real number between 0 and 1, what would it do? Computers can only use finite memory, so the number it spits out would always have a finite decimal expansion, a rational number. So no matter how hard you try, you will never, ever, by chance, pick one of the uncountably infinite irrationals or transcendentals. In a very real sense, almost every number in that interval is unpickable by any process that exists in our finite universe. But wait, there's more. In mathematics, probability is defined over intervals, not points, when we deal with continuous sets. If I ask, what's the probability that your number falls between 0.1 and 0.2? That's something we can measure, a tenth of the interval, or 10%. But the probability that you pick exactly 0.12345 with infinite decimal places is still 0. The very structure of probability theory buckles under the weight of infinity when we try to apply it to single points on the continuum. Now, let's throw in another layer, measure theory, the rigorous math behind modern probability. In measure theory, the measure, think of it as size or weight, of any single point in a continuous space is 0. This is why the probability is 0. Yet the measure of the whole set, the entire interval from 0 to 1, is 1. The sum of all the zeros over every single point somehow gives us a solid, tangible whole. Every point is measureless, but together they create reality. Think about the lottery. A lottery with infinite tickets, each ticket a real number between 0 and 1. If you try to pick the winning number, the chance you choose correctly is 0, but someone always wins. In fact, every time someone picks, they win, just not in the way we expect. The idea that something can happen even though its probability is 0, in this context, completely breaks our everyday intuition. The infinite choice trap is not just mathematical, it's psychological. It forces us to confront the limits of choice, the limits of chance, the limits of understanding. Let's push deeper into paradox. If every number has a probability of 0, but you always end up with some number, what does probability really mean in the infinite world? Does it mean anything at all? This isn't just a curiosity. It sits at the heart of quantum mechanics, chaos theory, and the most cutting-edge frontiers of science. The infinite choice trap is the reason why random number generators, lottery machines, and even physical processes cannot give you a truly random real number. The infinity is too deep, too overwhelming, too rich to ever be captured by finite means. And here's the most mind-bending part. Even if you tried to write down a random real number by hand, choosing each digit one at a time, your mind, your hand, your entire life's timeline, would run out before you ever completed the infinite sequence. Infinity, in this case, isn't just big, it's fundamentally unfinishable. The act of choosing from infinity is both possible and impossible, fated and forbidden, all at once. Why does this matter? Because every time you think about probabilities, about choices, about the spectrum of possibilities in life, you're touching the edge of this paradox. When mathematicians, physicists, philosophers talk about infinite sets, about the continuum, about the foundations of reality, they are wrestling with the infinite choice trap, this collision between the endless and the inevitable. We like to think of infinity as a playground for the mind, but it's also a trap for logic, a place where rules we trust break down, where common sense evaporates. The infinite choice trap teaches us humility. It shows that even the simplest questions, pick a number, any number, can unravel into bottomless mysteries when infinity is involved. So, next time you hear someone say, any number between 0 and 1, remember what's lurking behind that invitation. Remember the infinite ocean hiding in plain sight, the library of books you'll never even see, the numbers you cannot name or know. In the end, every choice you make in the infinite is a leap into the void, a brush with the absolute mystery that underlies mathematics and reality itself. And somehow, even though every point is impossible to choose, you still always choose something. That's the infinite choice trap, a riddle with no exit, and a mirror for the very limits of the human mind. The self-referential equation to curse. Imagine staring into a mirror only to see another mirror behind you, reflecting your image into itself, again and again, until the tunnel of reflections seems to stretch to infinity. The further you try to peer into the depths, the more you realize there is no end, and there was never a beginning. Now, what if I told you that mathematics, at its very core, harbors its own version of this recursive abyss, a curse woven into the fabric of logic itself? This is the curse of the self-referential equation. It sounds abstract, almost mystical, but it's real, powerful, and endlessly unsettling. Let's take a step back. Most equations behave the way you'd expect. You define x in terms of numbers or other variables, and with a bit of algebra, you untangle the mystery. But some equations don't want to be solved. Some equations don't just hide their answers, they loop you back into themselves, making you chase your own shadow. Imagine a simple equation like x equals sine 5. Clear, right? X is just 5. But what happens if you write x equals x plus 1? At first, it almost looks innocent. But pause, try to solve it, and you will quickly realize you're being pulled into an endless spiral. Subtract x from both sides, and you get 0 equals sine 1. Nonsense. You've torn a hole in arithmetic. But now, take it deeper. What if, instead, an equation references itself in its very definition, like a snake swallowing its own tail? Consider this. If x equals sine 1 plus fx, what could fx possibly be? If you try to solve for fx, you're forced to conclude f of x equals sine infinity, because no finite number can equal itself plus 1. The function slips from the realm of numbers into the realm of paradox. You might think these are just mathematical oddities, puzzles for bored mathematicians, but self-reference is a force that can upend entire systems. Think of the liar's paradox. This sentence is false. If the sentence is true, then it must be false. But if it's false, then it must be true. You've just entered a logical feedback loop, a hall of mirrors where every answer eats itself. When mathematicians tried to build the ultimate logical foundation for all of math, a project that reached its height in the early 20th century, they thought they could define every truth in mathematics from a few basic principles. But self-reference was a curse that refused to be exercised. In the early 1900s, Bertrand Russell found a fatal flaw in the very foundations of mathematics. He was trying to build sets, collections of objects, that could contain anything, even themselves. But then came the question, does the set of all sets that do not contain themselves contain itself? If it does, it shouldn't. If it doesn't, then it should. This self-referential paradox exploded the neat and tidy world that mathematicians had tried to build. Kurt Gödel took this idea further. In 1931, he published his incompleteness theorems, using self-reference as his key weapon. He built a statement in arithmetic that essentially says, this statement is unprovable. If the system could prove the statement, it would be inconsistent. If it couldn't, then the system was incomplete. Either way, self-reference cracked the very code of mathematical certainty. This isn't just high theory, it's everywhere in our digital lives. Computers, which run on logic, sometimes run into self-referential loops that cause catastrophic failures. Consider a simple command. If this statement is true, do nothing. If it's false, keep checking. The computer can end up in a loop, checking itself forever, stuck on the edge of meaning, unable to escape. Even in philosophy and language, self-reference is a minefield. Try to define definition without using the word define. Try to describe the act of describing. You will find yourself orbiting an empty center, caught in recursion. In human psychology, this is the basis for rumination, when thoughts endlessly circle around themselves, always referencing, never resolving. You think about thinking, worry about worrying, and become trapped in your own internal monologue. Self-referential equations have another sinister side. In computer science, this shows up in the halting problem, discovered by Alan Turing. Imagine a program that analyzes all other programs to determine if they'll ever stop running or loop forever. But then, what about a program that tries to analyze itself? You reach a point where logic shatters. The system collapses under the weight of its own self-awareness. This is not just theory. It's why your laptop might freeze on a blue screen, or why AI sometimes gets stuck in endless loops. But let's make this even more tangible. Think of a video camera pointed at its own screen. The image feeds back into itself, creating a vortex of repeating patterns, a visual echo chamber. The closer you look, the more intricate and unpredictable the feedback becomes. The same thing happens in mathematics. A self-referential equation creates a mathematical echo, a recursion that can never quite resolve. Now, let's explore a haunting real-world example. Fractals. The famous Mandelbrot set is defined by a recursive equation, z equals sign z2 plus c. The outcome at each step depends on the outcome before, cycling endlessly. Zoom in, and the pattern repeats, deeper and deeper, never ending, never beginning. The boundary is infinitely complex, forever folding back on itself. This is self-reference as art, a pattern so complex that it is infinite, yet created from a single simple rule that always loops back. But why does self-reference create such chaos? Because it destroys the comfortable separation between observer and observed, definition and defined. It refuses to let the system step outside itself. In logic, this creates paradox. In computers, it creates endless loops. In psychology, it creates obsessive thought. In philosophy, it shakes the foundations of language and meaning. We humans crave answers. We want to close the circle, find an endpoint, mark a starting place. But self-reference spits in the face of that desire. It tells us, sometimes, the circle is all there is. Sometimes, the very act of searching for the edge throws you back into the center. The self-referential equation is a lesson in humility. It shows us that not all mysteries can be solved by simply looking deeper. Sometimes, there is no deeper, just endless echoing. Sometimes, the question creates the answer, and the answer creates the question in an infinite dance. It forces us to accept limits, not of our intelligence, but of the very structure of logic itself. And so, where does the self-referential equation begin? Nowhere and everywhere. Where does it end? It doesn't. It only loops, echoing, reflecting, folding in on itself forever. If you chase it, you'll find yourself circling back to where you started, over and over, until the distinction between beginning and ending, question and answer, self and shadow, all blur into a single, endless recursion. Next time you stare into a mirror and see yourself staring back, remember, the universe may be doing the very same thing, forever defining itself in terms of itself, caught in an infinite recursion with no beginning and no end. The fair dice delusion. Close your eyes. Picture a die, just an ordinary six-sided die resting in your palm. Feel its weight, its edges, the cool certainty of geometry. Each face, 1 through 6, promises an equal chance. Roll it, and you trust. 1 in 6 odds, perfect fairness, a little pocket of order, inside a universe built on uncertainty. This is the dice you grew up with, the game piece you learned to trust. But what if I told you this trust hides a subtle illusion? What if, In chasing fairness, you end up confronting a deeper, more unsettling truth, that even in the purest randomness, patterns will emerge, and that these patterns are so seductive, so persistent, they threaten to convince you that chance is ruled by invisible laws, the fair die, the oldest metaphor for randomness. Each roll is a promise, 1/6 every time. Flip a coin, roll a die, shuffle a deck. Each is a ritual, a way of summoning chaos and taming it, briefly inside the human hand. You watch the die tumble, bounce, and finally rest. 4. Roll again. 2. Roll again. 6. The numbers feel wild, unpredictable, and yet, after enough rolls you start to notice something. Maybe you haven't rolled a 3 in a while, and a thought creeps in. It's overdue. Maybe you see the number 5 showing up 3 times in a row, and you feel the chill of suspicion. The die is loaded. Suddenly, you're no longer watching chaos. You're hunting for patterns. But what are you actually seeing? The mathematician's answer is clear. Every roll is independent. The die has no memory, no face is due. But intuition rebels. Our minds are wired to see streaks, to expect balance, to crave fairness, even when reality refuses to provide it. The fair dice delusion is born in this gap, between what we know is true and what we feel must be true. We believe in the fairness of the die, but after enough throws, we see patterns that feel like evidence of some deeper law, a law that perhaps isn't there at all. Let's break this down. Say you roll a die 60 times. Probability whispers, you'll get 10 ones, 10 twos, and so on. But roll the die for real, and you might get 15 sixes and only 6 fours. Suddenly the world looks skewed, and doubt creeps in. Is the die unfair? Or is chance simply rougher, wilder than you expected? Here's the paradox. The longer you roll, the more chance flexes its muscles. Clusters, gaps, streaks. These aren't signs of a broken system, but the natural noise of randomness. And yet, they look so much like rules. Now, stretch your imagination. Roll the die not 60, but 1,000 times. 10,000. 1,000,000. Now, patterns emerge with startling regularity. You will see long runs, 6 sixes in a row, or stretches of 30 rolls without a single one. In 1,000,000 throws, every face will have appeared thousands of times, but never exactly equally. Gaps remain. Streaks haunt the data. You might see 200 sevens before you see your next 5. The law of large numbers says that, as you keep rolling, the proportion of each number should settle ever closer to 1/6. And it does, but only in the limit. At every finite step, weirdness reigns. And now, the truly strange part, patterns are not evidence of order. They're evidence of chaos. In infinite randomness, every possible pattern eventually appears. Roll a die forever, and you will eventually see every imaginable sequence. One's repeating for 1,000 throws, then a perfect rotation through all 6 faces, then 1,000,000 sixes in a row. Not only can this happen, it must if you roll forever. The infinite monkey theorem applies. Given infinite rolls, the die will spell out any sequence you desire, order inside chaos. This is the heart of the fair dice delusion. We see clusters and gaps, and our minds whisper, this isn't random, something is controlling the die. But true randomness is wild enough to allow everything, even things that look planned. In a sea of chaos, order floats to the surface not as a violation, but as a guarantee. The more random you allow your world to be, the more strange, beautiful, and terrifying the patterns you see. Let's go deeper. Imagine a die with 1,000,000,000 sides. You roll it. The odds of getting any particular number are minuscule. Now roll it 1,000,000,000 times. Some faces will appear much more often than others. You start to suspect. Maybe the die is biased? But probability says the more sides, the more likely some faces will win by pure luck alone. The extremes become more extreme, not less. What feels like evidence of cheating is really just the math of infinity, but the illusion gets stronger. Casinos know this. So do magicians. The gambler's fallacy, believing that a run of reds on a roulette wheel means black is due, is just another face of the fair dice delusion. Our brains are wired for balance, for story, for symmetry. But randomness doesn't care about your sense of fairness. In the long run, fairness emerges in averages, not in every streak. If you keep rolling, the average outcome trends to the fair value. But the journey is bumpy, chaotic, forever full of jarring surprises. Yet, in a weird twist, randomness does submit to invisible laws. but not the ones you think. The law of large numbers tells us that as you roll the die more and more, the proportions of each outcome will approach their theoretical probability. The central limit theorem promises that sums of many dice rolls will create a bell curve, but in the details, randomness is not smooth. The path to fairness is rough, jagged, and unpredictable. So, is randomness ruled by invisible laws? Yes and no. The law is that, in the infinite, the patterns of the finite fade away. But in your lived experience, every run of dice, every game night, every streak will feel haunted by the possibility that chance is playing tricks. The truth is, randomness creates the illusion of order, because in a big enough mess, you can always find a shape, a story, a pattern. But these aren't the laws of the universe. They're the laws of your own searching mind. Here's the secret. The dice don't care. They never did. They tumble in silence, their faces ignorant of your hopes, your suspicions, your need for fairness. They are fair because they obey no law but physics. The only rules are the ones you create in your mind. The fair dice delusion is not in the die, it's in you. The more you search for order, the more chaos offers you patterns that mean nothing but feel like destiny. So, next time you roll a die, whether for a game, a bet, or just for wonder, remember this. The patterns you see, the streaks you fear, the gaps you doubt, are not signs of hidden hands or cosmic order. They are the fingerprints of chaos itself. A universe where even perfect fairness gives rise to illusions, and the only certainty is that, if you keep looking, you will always find something unexpected. The shape without dimension. Close your eyes and picture a coastline, jagged, wild, battered by the waves for 1,000 years. Imagine tracing your finger along its edge, from the wide curve of the bay to the razor-like inlets and outcroppings. The closer you look, the more detail you see. Crags within crags, stones within stones, each split by erosion into smaller and smaller features. Now, imagine you could shrink yourself down, smaller than a grain of sand, and continue your journey, measuring every new nook and crevice revealed at this microscopic scale. No matter how far you go, no matter how much you zoom in, the coastline never smooths out. It only reveals more and more complexity. How long is this coastline, really? Where does it end? Welcome to the world of fractals, the shapes that twist the logic of dimension and defy our deepest intuitions about space and measurement. A fractal is not just a mathematical curiosity. It is a window into a realm where the ordinary rules of geometry break down and the impossible becomes strangely real. In a fractal, you encounter a paradox. A line that loops and turns so wildly that its perimeter is infinite, yet the area it encloses remains perfectly finite. How can a boundary be endless when the space it wraps around is so tame? This is the shape without dimension, a border that stretches forever, packed into a space that refuses to grow. To truly feel the strangeness, let's travel into the heart of the most famous fractal, the Mandelbrot set. On a screen, it looks like a warped snowman, a black body ringed with electric fire. But the magic is not in its outline. The magic is in the infinite. Zoom in anywhere, onto one of the spiny arms or a swirl at the edge, and the pattern repeats. Smaller versions of the whole emerge, dancing forever at every scale. No matter how deep you go, you never reach the end. The boundary writhes and coils with infinite detail, a universe hiding inside a speck. Think of another classic, the Koch snowflake. Begin with a triangle. Divide each side into thirds, build a smaller triangle on each middle third, and repeat forever. After just a few steps, the edge is jagged. After a dozen, it's wild and spiky. If you could repeat the process infinite times, the snowflake's perimeter would stretch out infinitely long, yet the area it encloses would never exceed a fixed limit. It's as if you could build a fence of infinite length around a garden no bigger than your backyard. This is not just mathematical poetry. Fractals reveal a strange crack in the foundation of dimension itself. Normally, we think of a line as one-dimensional, a plane as 2, a solid as 3. But fractals exist in the shadows between these numbers. The edge of the Mandelbrot set, the border of a snowflake, the outline of a real coastline, they all have fractional dimension, a ghostly in-betweenness that mathematics calls fractal dimension. It is neither a line nor a plane, neither finite nor infinite, but a blend of both, a shape that never truly resolves. Why does this matter? Because fractals are everywhere, woven into the fabric of nature and the algorithms of human invention. The veins of a leaf, the branching of a tree, the arteries in your body, the patterns of clouds and mountains and lightning. Each follows a logic of endless division, of complexity blooming out of simplicity. Even our brain's neural networks and the financial markets we build pulse to the rhythm of fractal geometry. Every time you look at a fern or the lacy structure of a snowflake, you're glimpsing the hidden mathematics that shapes the world. But now, the question grows stranger. Where does a fractal actually exist? Is it real, or only a product of the mind, an artifact of mathematical imagination? You can draw a fractal on a piece of paper or see one generated by a computer, but you can never fully capture it. No computer can hold all the infinite detail. No pen can trace every twist and curl. Even the coastlines and clouds and trees of the natural world are only approximate. Nature starts the fractal, but reality eventually runs out of atoms. And yet, the idea of the fractal boundary, the infinite within the finite, remains. It's as if these shapes occupy a secret dimension, one not fully present in the material world, but haunting its edges. They are blueprints for endlessness, scripts for complexity written into the language of mathematics itself. The fractal never quite exists in the physical sense, yet its logic is so compelling that we find it echoed all around us, from the structure of galaxies to the tiniest grains of dust. Let yourself dwell on the paradox. In our minds, we can always zoom deeper and always discover new detail, always divide again. But in the real world, eventually, you'll find yourself up against the grain of sand, the atom, the quark. Infinity is an idea, an abyss at the heart of mathematics and perhaps of consciousness itself. The fractal, then, is a symbol, a doorway between the finite and the infinite, the possible and the impossible. So next time you look at the edge of a leaf, or the foam at the shore, or a lightning bolt carving its way through the sky, remember that you're staring into a shape without dimension, an infinite journey packed into a finite moment. Fractals remind us that reality is richer, wilder, and far more mysterious than any rulebook suggests. They invite us to question not only where they exist, but where we exist, somewhere on the boundary between order and chaos, between the infinite and the real, tracing patterns in a world whose edge never truly ends. The mirror symmetry collapse. Imagine a world built entirely from reflections. Mirrors in every direction, surfaces so perfect they swallow light and spit it back, images chasing themselves in endless corridors. The mind stumbles into these infinite mirror worlds, expecting logic, expecting order, expecting that everything reversed should be perfectly, symmetrically true. But what if reflection is a liar? What if, hidden within every mirror, there's a secret boundary, a line where truths quietly dissolve, where meaning collapses with the flip of an image? Tonight, we step into the silent heart of the mirror symmetry collapse, where reflection and reversal are not the same, and some truths vanish when the world is flipped. Let's begin simple. Hold up a number, 123. Reflected in a mirror, you see 321. The order is reversed, but it's still a valid number, still meaningful, still familiar, just backwards. Now, try a word. Dog becomes God in the mirror. A new word appears, sometimes meaningful, sometimes nonsense. In both cases, you expect that what goes in comes out mirrored but intact. But let's go deeper. What if you hold up a number like 689? In the mirror, the 6 becomes a 9, the 9 becomes a 6, but the 8 remains the same, strangely untouched by reflection. You realize not every symbol survives the flip in the same way. Some digits, like 2 or 5, become distorted, unrecognizable, or simply not themselves. The deeper you go, the more cracks appear. But this isn't just about numbers or letters on a page. The illusion reaches into the core of mathematics and physics, revealing a paradox that unsettles the foundation of what we call symmetry. Reflection, after all, is not reversal. To reverse is to travel backward along a line, to retrace steps, to unspool time itself. To reflect is to swap left and right, to invert a world without ever moving forward or back. They feel similar, yet their consequences are worlds apart. Consider the classic example. The mirror image of your right hand is a left hand. The hands are shaped the same, but they cannot be laid atop one another, no matter how you turn them. One is the mirror, the other is the original. The The same applies to shoes, to gloves, to molecules. In chemistry, some molecules are chiral. They exist in two mirror image forms called enantiomers. One form might heal, the other might poison. Their structures are identical except for the mirror, flip, but their effects on life are absolutely not the same. The mirror world is similar, but not identical. In reflection, things that should be the same are fundamentally, irreconcilably different. Now look at mathematics itself. Think of the number line. Positive numbers stretch infinitely to the right, negatives to the left. If you reflect the number 5 over 0, you get -5. In a sense, you've performed a reversal, but some truths vanish in the flip. For example, the square of 5 is 25. The square of -5 is also 25. The sign, positive or negative, is erased by the operation. Symmetry is preserved in the result, but lost in the journey. If you reflect a function, a process, a sequence, sometimes you find the pattern survives. Sometimes it crumbles into noise. Certain equations are invariant under reflection, unchanged, untouchable. Others fracture, losing all sense. Let's dive deeper. Imagine you're navigating a maze with perfectly mirrored walls. Every turn you make, every decision, is immediately doubled, reflected, replayed in the opposite direction. If you try to reverse your steps, you can find your way back. But if you step through the mirror, suddenly the world is alien. Left becomes right, clockwise becomes counterclockwise. Even the laws of physics don't always play fair in the mirror world. In 1956, physicists discovered that the universe itself is not perfectly symmetric. In certain radioactive decays, specifically the weak nuclear force, nature violates mirror symmetry. If you watch these processes in a mirror, you'd see an impossible event, something that simply cannot occur in our universe. The reflection is not just different, it's forbidden. Reality picks a side. This is where the collapse happens. We expect the world to be fair, to be consistent, to honor symmetry in every dimension. But the deeper laws refuse. Some truths, when reflected, disappear entirely. Imagine writing an equation in the sand, then seeing the ocean erase half of it, never to be recovered. That's the feeling of mirror symmetry collapse, an intuition torn apart by hidden rules. The effect bleeds into daily life too. Language is full of palindromes, words and sentences that read the same backward and forward. Race car, madam. There's a thrill in finding these rare islands of perfect symmetry, but they are rare for a reason. Most truths are not so forgiving. Reverse the letters in truth, and you get turt, a word without meaning, a sound that evaporates as soon as it's spoken. The collapse is everywhere. You try to build meaning out of reversal and reflection, but most of what you create falls apart in your hands. Let's get abstract. Picture the world of logic and philosophy. Imagine two statements, if A, then B, and if B, then A. They look symmetrical, but they are not equivalent. The truth only runs one way. Mirror them, and the relationship shatters. Even in human memory, reflection is not reversal. You can recall the past, but you can't live it backward. The sequence of events, once mirrored, loses context, emotion, meaning. A photo in a mirror shows a familiar face, but the parting of the hair, the angle of the smile, is subtly, uncannily wrong. You recognize yourself, but something essential is missing. You are not your own reflection. So, why does this matter? Why should you care about mirror symmetry collapse? Because it's a crack in the foundation of reality. A reminder that not every reversal is a restoration, not every reflection is a return. There are processes in the world, and in your own life, that cannot be undone simply by flipping them around. Mistakes, words spoken, moments lost, these cannot be reversed, only reflected, and even then the result is never truly the same. The universe is not a perfect palindrome. Mathematicians and physicists chase symmetry because it promises certainty, predictability, a sense of control over chaos. But in every equation, there are conditions, boundaries where symmetry ends and collapse begins. The mirror is not a doorway to an equal world, but a portal to a subtly different one, ruled by its own logic. When you encounter a moment that seems unfair, a truth that dissolves when flipped, remember the lesson of the mirror. Not every reversal restores, not every symmetry holds. Stand again before the endless mirrors. Watch as your image multiplies into infinity, but know that each copy is just a ghost, a surface truth, never the substance. Some truths survive reflection, many do not. And somewhere, between left and right, real and reflected, lies the silent line where meaning collapses. The mirror never lies, but it never tells the whole truth either. The area under nowhere. Close your eyes and picture a graph, a simple X and Y axis, a blank canvas waiting for meaning. Now imagine drawing a function, one so wild, so broken, that it doesn't even touch the page in any smooth way. A function made of pure spikes, like static on a TV with no signal. Its values flickering violently between 0 and 1, never lingering, never forming a shape you could follow. You stare at it and see nothing. No smooth curve, no area, nothing you could ever measure or shade in. This is not art, this is mathematical chaos. Yet, here's the trap, the impossible twist that turns all your intuition inside out. Take this nowhere curve and perform the act mathematicians call integration, summoning the ghostly machinery that calculates the area under the curve. You expect to get nothing. How can there be area where there is no substance, no stretch of stability, no foothold for measurement? But as you integrate, something shocking happens. Out of the chaos, area appears. Not as a smooth, sensible expanse, but as a shape conjured from nowhere, an unexpected, paradoxical result. Suddenly, a curve made of spikes, a function that seemed to have no area at all, is revealed to contain smoothness that nobody asked for. This is the mystery of the area under nowhere, a paradox so deep that it challenges the foundations of mathematics, logic, and even our sense of what it means for something to exist. It's not just an abstract puzzle for professors, it's a trapdoor lurking beneath the world of calculus, a shadow at the heart of every equation that tries to measure the unmeasurable. Let's make this tangible. Picture the Dirichlet function, a classic monster of mathematics. Here's how it works. For every rational number on the x-axis, the function jumps to 1. For every irrational number, it crashes to 0. There are infinitely many rationals and even more irrationals, all densely tangled between 0 and 1. The result is a graph that looks like static. No line, no shape, just infinite dust-like points. Now try to find the area under this function between 0 and 1. If you shade in all the points where it's 1, you'd expect to get some area. But those points, despite being infinite in number, have no width. They are scattered too thinly, like sand blown across a desert so wide the grains can't cover anything. When you try to sum their area, you get 0. But here's where the paradox deepens. Take a different function, say the Cantor function, also known as the devil's staircase. This is a function that never increases on most of its domain, yet somehow, from 0 to 1, it rises from 0 to 1 in a series of sudden jumps, all while being perfectly flat almost everywhere. If you try to calculate the derivative of this function at most points, you get 0. But when you integrate, when you ask how much area lives under this staircase, you find it's not 0. There's a full unit of area, perfectly matching the rise of the staircase. A function that is motionless almost everywhere somehow sweeps out an area, a ghostly presence emerging from mathematical stillness. Think about what this means. Our entire intuition about area under the curve comes from childhood. If you draw a smooth arch, shade under it, and count the squares, you get an area. But these functions break that logic. Their graphs are so jagged, so disconnected, that no ruler, no paintbrush, no digital pixel can capture their substance. They are made of points that individually take up no space. But together, by some infinite collaboration, they manage to conjure a shadow, a measurable presence where nothing seems to be. This isn't just a mathematical trick. It's a deep lesson about how complexity hides in plain sight. It's as if you walked into a room that appeared empty, but when you shined the right kind of light, ghostly forms appeared all around you, forms you never knew were there. That's what integration does. It reveals the hidden skeleton beneath chaos. Let's go deeper. Take the idea of a function that is 0 everywhere except at a single point. Say, at x equals 0.5. At that one point, the function leaps up to infinity. This is the Dirac delta function, a mathematical tool that, for most people, shouldn't exist. It has no width. But if you integrate it, if you ask how much area lies under this infinite spike, the answer is exactly 1. It's like having a wall with no thickness, but when you measure it, you find it blocks a solid slab of reality. This is the mathematics of paradox, where integration finds substance where there is none, and area where there is nowhere. In probability, this idea gets even stranger. Probability density functions can be made of spikes, gaps, or nowhere at all. But when you integrate them, when you ask, what is the chance of something happening in this interval? Suddenly, out of the mathematical void, probability appears. The area under nowhere is the very foundation of how randomness is measured, how quantum mechanics works, how nature encodes information. It's tempting to dismiss this as ivory tower madness. But think about the stock market. Prices jump in spikes, seemingly random and disconnected. Yet, when economists integrate over time, they find trends, patterns, even a kind of smoothness emerging from chaos. Think about music. Digital audio is made of sharp, spiky samples. But when you integrate those samples, you hear smooth melodies and waves. This paradox matters because it exposes the limits of human intuition. We trust our eyes, our hands, our experience. But mathematics shows us a world where the invisible can add up to the tangible, where nowhere can become somewhere, where a curve of chaos can hide a secret reservoir of smoothness. There's a quiet terror here, too, a sense that reality is built from pieces we cannot see, that every smooth thing we trust might be hiding a fractal skeleton, a wild dance of spikes just beneath the surface. Integration is not just addition, it's revelation, a way of seeing the world that exposes the secret connections binding the disconnected, the order inside disorder. The area under nowhere reminds us that mathematics is not just about numbers, it's about the nature of existence itself. It's a tool that pulls substance out of emptiness, that finds form in the formless, that challenges everything we think we know about what can and cannot be measured. So the next time you see a graph, a curve, or even a moment of chaos in your life, remember the lesson of the area under nowhere. Remember that smoothness can emerge from spikes. That area can be hidden in what appears to be nothing at all. In the end, the universe itself might be built on these paradoxes, on the sudden, shocking appearance of substance in the places we'd sworn were empty. And as you walk through your own days, remember, sometimes the most powerful realities are the ones hiding just beneath the surface, waiting to be revealed by the simple act of seeing in a new way. That is the area under nowhere, a silent miracle, a mathematical ghost, a reminder that reality is stranger, deeper, and far more mysterious than anyone ever expected. The imaginary number infection. Close your eyes and imagine a number that isn't supposed to exist. A number so strange, so alien, that it literally calls itself imaginary. Not negative, not positive, not even zero. Something that sits off the number line, neither here nor there. For most of human history, mathematics banished such numbers to the realm of absurdity. They were the offspring of equations no one could solve, the infection that spread whenever you tried to take the square root of a negative number. Logically forbidden, philosophically exiled. But what if I told you that these so-called imaginary numbers don't just haunt the edges of math? They quietly define the rules of our reality, whispering behind the scenes of everything from electricity to the very core of quantum physics. And if reality is built on the backs of what's unreal, how do you ever know what's true? Let's rewind to a time before imaginary numbers. In school, you're taught there's no real solution to the equation x2 equals sign. 1. It's not just hard, it's impossible. Square any real number, positive or negative, and the result is always positive. Negative numbers can't have real square roots. The math teachers tell you, move along, there's nothing here. But then, somewhere in the 16th century, mathematicians refused to look away. They gave this forbidden root a symbol, I, the imaginary unit, where I2 equals sign 1. Just like that, the gates to an impossible kingdom creaked open. But the moment mathematicians accepted I, their equations caught an infection that couldn't be contained. Suddenly, complex numbers, numbers with a real part and an imaginary part, began to emerge everywhere. At first, people mocked them. Imaginary? You might as well chase the square root of a unicorn. Even the greatest minds doubted their reality. René Descartes coined the name imaginary as an insult. Yet, mathematics is relentless. If something works, it stays. If it solves problems, it survives. And it worked, far better than anyone could have guessed. Suddenly, problems that had been unsolvable became trivial. Equations that stymied generations snapped open like magic boxes. The infection spread into physics, engineering, and beyond, But how can something unreal become so indispensable? Let's take electricity. Every time you turn on a light, charge your phone, or power a city, you're dealing with alternating current, AC. The flow of electrons oscillates, moving back and forth in perfect rhythm. But real-world systems, circuits, resistors, capacitors, are governed by equations that become tangled knots without imaginary numbers. Using I, engineers can represent alternating voltages and currents as spinning vectors, called phasors, that slice through the complex plane. Calculations that would be impossible become simple. Your entire power grid works because we trusted the unreal. Now step deeper into quantum physics. Here, imaginary numbers don't just help. They're at the center of the dance. Schrödinger's famous wave equation, which predicts how electrons move, is built around I. The wave function, a ghostly, probabilistic ripple that describes the state of a particle, isn't real or imaginary, but complex. To calculate probabilities, physicists multiply wave functions by their complex conjugates, spinning reality through the imaginary dimension to extract what's real. Strip I from quantum mechanics, and the whole theory collapses. But the paradox grows darker. Imaginary numbers also haunt signal processing, audio synthesis, and even your smartphone's touchscreen. Every time your device processes sound, images, or data, it uses algorithms, like the fast Fourier transform, that rely on the complex plane. Without I, no music, no calls, no internet, no simulation. But if imaginary numbers are so vital, why do we call them imaginary? Why the lingering suspicion, the lingering sense that we're cheating reality? It's because they threaten the boundary between what's tangible and what's abstract. You can't hold it in your hand, can't mark it on a ruler, can't find it on the number line. It's a ghost. A mathematical hallucination that somehow drives the machinery of the world. This infection is unsettling. It means that the universe, at its core, runs on a logic stranger than anything you can touch or see. It suggests that the simulation we call reality is built from layers deeper than sense or measurement. What else lurks below the surface, disguised as unreal, but controlling everything? Are we living in a universe that needs ghosts in its machine? Or are imaginary numbers hints of another dimension, a hidden axis, invisible but essential? This isn't just an academic question. The real and the imaginary combine to form the complex plane, a two-dimensional world where every number is a point, not just a spot on a line. Here, multiplication becomes rotation, and equations become geometry. Visualize the Mandelbrot set, a fractal so intricate and beautiful it seems to contain infinity within itself. Its entire structure is defined by complex numbers, spiraling between the real and the imaginary. The most profound art of mathematics is born from the infection we once tried to quarantine. Think of Euler's identity, often called the most beautiful equation in mathematics. E-IP plus 1 equals sign 0. In one breathtaking line, it ties together exponentials, pi, 0, 1, and, most shockingly, the imaginary unit. This isn't mere coincidence. It's a glimpse of something profound. Reality itself woven from contradictions, blending the real and the unreal, the visible and the invisible. So, can you trust what's unreal? Can you trust a number that shouldn't exist, but somehow rules over what does? The lesson of the imaginary number infection is that the boundaries between real and unreal are softer than we think. The world isn't made from what you can see or measure, but from the logic and language that let you make sense of it at all. Sometimes, what seems impossible is merely waiting for you to expand your imagination. Next time you flip a switch or listen to music, remember, you owe your moment of reality to the silent presence of something imaginary. In the end, perhaps, the unreal is more real than anything you'll ever touch. The infection is complete, and reality, it turns out, is stranger than fiction. The infinite loop, integral. Picture a mathematician alone at midnight, staring at a blackboard tangled with infinite sums. They begin with a wild idea. What if you could add together an infinite list of numbers, each stretching out forever, and the result was not an explosion into infinity, but a clean, finite answer, a perfect, impossible balance snatched from chaos? This isn't a dream. It's the reality of infinite series and the logic that shapes the very edge of what we know as mathematics. But just as the mathematician begins to trust this power, they stumble upon a chilling paradox. Change the order of those infinite numbers, and reality itself seems to warp. The sum twists, mutates, even explodes. Infinity, it turns out, is not just big. It is sensitive, unpredictable, and sometimes shockingly fragile. The infinite loop. Integral begins simply. Imagine this. Take the series 1, 1 plus 1, 1 plus 1, 1, forever. What's the sum? If you group the terms like 1, 1, plus 1 and 1 plus 1, 1, you get 0. But if you start with 1 plus 1 plus 1 plus 1 plus 1, you get 1. Is it 0? Is it 1? Or something else entirely? With finite sums, order doesn't matter. But infinity laughs at order. The deeper you go, the less the usual rules apply. Now, think of the series 1, 1/2 plus 1/3, 1/4 plus 1/5, 1/6. This is the famous alternating harmonic series. It creeps, shuffles, and balances its way toward a very specific finite value, the natural logarithm of 2. If you add enough terms, the sum hovers ever closer to this number, never reaching, always approaching, always converging. Here, infinity seems tame, domesticated by alternating signs, by a rhythm of giving and taking. But the darkness waits just beneath this order. Because here's the twist. Take those same terms and shuffle them. Instead of strictly alternating positive and negative, sprinkle a few positives, then a negative, then more positives, then a negative. In fact, with careful choice, you can force the infinite sum to add up to any value you want. 2, 1,000, or even infinity itself. Rearranging the order of infinite terms lets you shape reality. This is Riemann's rearrangement theorem, one of the most mind-warping facts in mathematics. For some infinite series, the sum is not fixed, but can be bent and reshaped by the order in which you add the numbers. It's as if you built a tower out of blocks, blue, red, perfectly balanced. But if you change the stacking order, suddenly your tower bends, grows sideways, or stretches toward the sky. Infinity obeys, but with a price, you lose the certainty of arithmetic. What was once a law, the sum of numbers is always the same, no matter the order, dissolves in the endless. The mathematician faces a new terror. Math, the purest science, breaks when confronted with infinity and order. The ground shifts, rules bend, intuition vanishes. Let's take it further. In calculus, integrals can sum up infinite slices of an area under a curve. When all the slices are positive or all negative, or if their absolute values sum to something finite, order does not matter. The sum is called absolutely convergent. These are safe, predictable, stable. But not all infinite series are so forgiving. If the positive and negative slices balance in a precarious dance, never fully dominating, always in tension, the sum can depend on the order you take them. Change the sequence, change the answer. The boundary between order and chaos is thin and trembling. Imagine an artist painting an infinite mural, one brushstroke at a time. If they alternate light and dark in a careful, precise pattern, the picture resolves into a recognizable shape. But if they begin to lay down long streaks of light, then sudden bursts of dark, the picture mutates. Rearrangement creates meaning, or destroys it. In the universe of infinite series, the artist is not always in control. Sometimes the mural paints itself, revealing order only when viewed from a certain angle. Now is step into the heart of physics. The world itself, on the tiniest scale, is shaped by infinite sums, quantum fluctuations, probabilities, waves adding and canceling in endless superpositions. Physicists learn the hard way that order matters when taming infinity. In Feynman diagrams, in the calculation of quantum fields, the arrangement and renormalization of infinite terms can change the prediction itself. What should be solid becomes liquid. Infinity is not a gentle expanse, but a churning sea, waiting for any slip of order to swallow logic whole. Here's a haunting example. Imagine adding up the numbers 1 minus 1, 1/2, 1/2, 1/3, 1/3, and so on, for always a positive and its negative. What if you add all positives first, then all negatives? The sum balloons to infinity, then crashes to negative infinity. But alternate them carefully, positive, negative, and the sum remains stable, finite, converging to zero. The act of rearrangement is not innocent. Infinity remembers every choice you make. This is the infinite loop integral, not just an endless sum, but an endless trap. It tempts you with the illusion of order, then punishes you for forgetting that order is a choice, not a law. It's a window into the wildness at the foundation of mathematics, a place where infinity obeys, but in obedience reveals its power to destroy certainty. But why does this happen? At its core, mathematics for the finite is built on commutativity, the idea that you can rearrange terms in a sum, or steps in a calculation, and always get the same result. With infinity, this commutative law collapses. For some series, this is fine. Absolutely convergent series keep their secrets no matter the order. But for conditionally convergent series, those barely balanced on the knife's edge, the result is as fragile as a house of cards in the wind. Order, suddenly, is everything. The philosophical shock is deep. In math, we search for truth, for certainty, for the promise that calculation brings knowledge. But infinity shows us the limits of reason. If you trust only in the finite, your rules hold. If you reach for the infinite, the very idea of a rule dissolves, and with it, the dream of perfect knowledge. So next time you see an infinite sum, a formula stretching out across the horizon, a series reaching beyond the stars, remember that its value is not only a matter of magnitude but of order, of choreography. The dance of infinity is wild, untamed, and full of secret rules you only glimpse when you dare to shift your point of view. Infinity, in the end, is not just endless, it's listening always to the order in which you call its name. And if you're not careful, it will answer with something you never expected. In this way, the infinite loop integral is not just a mathematical trick, it is a warning that some truths are forever out of reach, that the infinite may obey you, but only if you respect its power. Math breaks, not in the face of numbers, but in the endlessness that refuses to be pinned down, an eternal reminder that order, in the infinite, is never guaranteed, and certainty is only an illusion. The Cantor diagonal reversal. Picture yourself trying to write down every possible decimal between 0 and 1. You're determined, focused, perhaps even a little obsessed. You start a list. 0.1, 00000, 0.1, 41592, 0.333333, 0.999999. Each decimal seems to fit neatly onto the page, each one another slice of the infinite. As your list grows, you feel a strange confidence. Maybe, just maybe, you can capture them all. Maybe infinity for once will submit to order. But then, just as your list stretches further than you can see, a quiet rebellion begins. A ghostly number sneaks through the cracks, one that can't be found anywhere on your list, no matter how long you make it, no matter how many decimals you try to squeeze into order. You start to realize that something fundamental about infinity defies you. It slips away, reshaping itself every time you think you have it cornered. This is the heart of the Cantor diagonal reversal, a paradox that shattered the world of mathematics and exposed the wild, untamable spirit of infinity. The story begins with Georg Cantor, a mathematician who dared to ask a forbidden question. Can we count infinity? Can we take all the real numbers, or all the decimals between 0 and 1, and put them into a list, one after another, so that none are left behind? At first, it feels like a question of discipline, of persistence. If you can list all the whole numbers, why not all the decimals? After all, decimals are just endless sequences of digits. Shouldn't they too line up obediently, ready to be counted? But Cantor saw something different, an abyss in the logic. He devised a method so simple, yet so powerful, that it destroyed the illusion of order forever. Imagine your list. Each row is a decimal, stretching infinitely to the right. Now, draw a line down the diagonal, taking the first digit of the first decimal, the second digit of the second, the third of the third, and so on. For each digit you find, change it. If it's a 3, write a 7. If it's a 9, write a 2. Do this for every digit along the diagonal, and you create a new decimal, one that is guaranteed to differ from every number in your list, at least in one place. No matter how many decimals you write, this outsider will always evade capture. It's the unlistable, the ever-escaping fugitive of the infinite. This is the Cantor diagonal reversal, a method that proves with chilling elegance that infinity is not all the same size. The set of all natural numbers, 1, 2, 3, on and on, is infinite, but it's a tamer infinity, one you can count step by step. The decimals, the real numbers between 0 and 1, are something else entirely. They form an infinity so vast, so intricate, that no list, no system, no attempted order can ever contain them. For every list you build, there's always a gap. Always a new number lurking outside, built with the diagonal method, forever beyond your grasp. Think about what this means. If you try to capture all possible passwords with infinite length, or every possible path in a quantum universe, the diagonal method whispers that you'll always miss one. Even in your wildest dreams of control, infinity slips away, ensuring an outsider always exists. It's a mathematical rebellion, a proof that there are more things in heaven and earth than are dreamt of in your philosophy. But the paradox runs deeper. The diagonal method doesn't just reveal a missing number, it exposes the raw, terrifying creativity of infinity. No matter how complete your system, how perfect your logic, infinity resists completion. It shatters any illusion of mastery. It's like trying to catalog every possible story, every possible life, every possible moment. For every attempt to list them all, there is always a new story, a new person, a new universe that escapes the net, a diagonal creation, always one step outside the box. The implications ripple across mathematics, philosophy, and even physics. If you believe the universe is a vast but finite machine, then perhaps everything can be listed, ordered, completed. But if you believe in the untamable infinity revealed by Cantor, then there will always be more. Always an outsider, always a new creation. Even the idea of consciousness or identity becomes suspect. Are we just one of the listed possibilities, or are we the outsiders, born from the diagonal, refusing to be contained? In computer science, the diagonal argument becomes a weapon against arrogance. It proves that not all problems can be solved by algorithms. There are functions that can never be computed, truths that can never be listed, answers that will always escape the net. The Cantor diagonal reversal isn't just a quirk of numbers, it's a warning, a humbling reminder that the world is stranger, wilder, and more infinite than our minds can grasp. So, next time you try to list everything, to bring order to chaos, remember the diagonal. Remember that for every list, there's a shadow, a hidden outsider built from the very fabric of the list itself. Infinity does not submit. It does not end. The diagonal method ensures that, no matter how far you reach, something will always slip through. A new number, a new idea, a new infinity, waiting for you on the other side. Infinity resists completion. It resists finality, refuses your lists, breaks your logic, and dares you to dream even bigger. The Cantor diagonal reversal is the ultimate rebellion, a proof that, in the endless sea of possibility, there will always be something more. And so, the journey through infinity continues, with the diagonal as your eternal companion, forever guiding you just beyond the edge of the possible. The paradox of measure zero. Picture the endless stretch of the real number line, a horizon that never bends, never loops, stretching out into eternity in both directions. Every point on this infinite line, every possible decimal, every fraction, every irrational number, every elusive value between values, exists with relentless, seamless continuity. There are uncountably infinite points, more than the stars, more than the grains of sand, more than the atoms in the universe. Now imagine a ghostly hand reaching out to cover this infinite line, not with a thick blanket, not even with a thin thread, but with a set so delicate, so sparse, so mathematically fragile that it's said to have measure zero, to take up no space at all. Yet, in a twist that breaks intuition, this set somehow manages to cover the entire real number line, leaving nothing exposed. Welcome to the paradox of measure zero, where nothingness becomes everything, and the world of size and substance dissolves into pure abstraction. Begin by asking, what does it mean for something to have measure zero? In the ordinary world, if you cover a line with a rope, the rope has length. You can measure it. Cover a floor with a sheet, the sheet has area. Even the thinnest wire, the tiniest speck, has some positive size. But in mathematics, especially in the mysterious realm of set theory and analysis, there exist sets so slender, so vanishingly small, that they are considered to take up no space at all. Their measure, the mathematical notion of size, is zero. Think of a single point. Its length is zero. A finite set of points? Still zero. Even an infinite set of countable points, like the rational numbers, has measure zero. These sets are ghosts, present, real, but ungraspable. But here's where the paradox begins to take form. What if I told you there exist sets, constructed with terrifying precision, that can cover the entire real number line, yet their measure is zero? It sounds like magic, or a cheat. But it's the result of mathematical logic, wielded with the sharpness of a surgeon's knife. The most famous example is the Vitali set, a set so strange, so fundamentally non-constructible that it cannot even be explicitly described, only proven to exist by the machinery of the axiom of choice. This set, and others like it, can be built so that every real number is within some translation of this measure zero set. You could shift it, slide it, and every possible value along the number line will be touched, yet the set itself, in its original form, still has measure zero. You've covered everything, using nothing. To make this more concrete, let's step back and imagine another paradox, the Cantor set. Start with a line segment, say from 0 to 1, remove the middle third. Now, from what's left, remove the middle third of each remaining segment. Repeat this process forever, always removing the central third from every surviving fragment. In the end, what's left is a fractal dust of points, the famous Cantor set. Here's the paradox. You've removed so much that the total length left is zero, yet the set still contains infinitely many points, as many as the whole line segment you started with. This set again has measure zero. It is nothing and everything, an infinite population occupying no space. But the real punch comes with the realization that, in higher mathematics, you can construct measure zero sets that, through clever rearrangements, translations, and combinations, can cover the entire real line. These sets are not solid, not connected. They are like mathematical mist, able to soak through every crevice without ever becoming thick enough to measure. This is the collapse of intuition. You thought that nothing couldn't become everything, but the world of sets has no obligation to obey common sense. The paradox of measure zero forces us to reconsider what it means to cover or occupy space. In the physical world, something must have extension, volume, or area to matter. But in pure mathematics, covering can mean that every point, every value is accounted for by a translation of a set with zero size. Nothingness becomes omnipresent, dissolving the boundary between presence and absence. Think about the implications. Imagine trying to paint every point on a wall with a brush that has no width, no bristles, just an abstract, ghostly contact. In the physical world, you'd fail. But in mathematics, the wall can be completely covered by such a brush. It's not just counterintuitive, it's almost terrifying. It tells us that size and coverage are not the same thing, that reality is far more nuanced than the eye or even the mind can grasp. Even more unsettling is how measure zero sets underpin the chaos of probability, randomness, and the theory of integration. When you pick a real number at random between 0 and 1, the chance of picking any specific rational number, despite there being infinitely many, is zero. The rationals form a set of measure zero. They're everywhere, densely woven, and yet, in terms of size, they're nothing at all. This is why the paradox of measure zero is so profound. It exposes the soft underbelly of mathematics, the place where substance evaporates into structure, and where the most delicate of sets can wield the power to cover the infinite. It is a world where infinity and zero dance in perfect, invisible synchrony, a world that, at first glance, looks empty, but on closer inspection, contains the universe itself. Next time you imagine a line, a continuum, or a space filled with possibility, remember, nothingness can be everywhere. The things you cannot see, cannot measure, cannot touch. These are sometimes the very structures that form the fabric of the mathematical world. The paradox of measure zero is a reminder that, in the realm of pure thought, everything and nothing are just two faces of the same infinite coin, flipped endlessly in the silent darkness beyond intuition. The infinity ladder paradox. Imagine yourself at the base of an endless staircase, the kind that disappears into the clouds above. Each step is smaller than the last, but no matter how many you climb, the top always lies just out of reach. This isn't just a metaphor. It's a mathematical paradox, one that invites us to wrestle with the very nature of infinity and the human urge to measure what can never truly end. Let's begin at the first rung. You take your first step. 1. It's solid, concrete, the foundation. Now, add half a step more, 1/2. It's smaller than the first, but you feel yourself rising. Add another, this time just a third of a step, 1/3. The staircase stretches ahead, each rung a fraction tinier than the last. 1/4, 1/5, 1/6, and so on, forever. The paradox is simple to state. Keep adding, keep climbing. The total, the sum of this infinite sequence, grows and grows, reaching heights unimaginable. But here's the twist that bends your intuition. It never, ever becomes infinite. It grows forever, but never explodes into true infinity. This is the infinity ladder paradox, born from the harmonic series, 1 plus 1/2, plus 1/3, plus 1/4 plus, an endless sum that tantalizes with its promise of infinity, yet always remains just out of reach. For centuries, mathematicians, philosophers, and dreamers have stared at this ladder, haunted by its riddle. How can something that never ends also never arrive? How can eternity be measured, yet never completed? Let's make it more concrete. Suppose you decide to walk this ladder in the world of numbers. After the first step, you're at 1. Take one more, and you're at 1.5. Add the next, and you're at 1.833. Each new step lifts you, but the rise grows slower and slower. After 10 steps, you're at just under 3. After 100 steps, a little over 5. After 1,000, you've barely touched 7. It feels like the staircase is flattening out, slowing to a crawl. But watch closely. No matter how long you climb, the staircase never stops rising. There is always another fraction to add, always a higher step. The sum never settles, never levels off, never forms a ceiling. This is where the paradox bites deepest. Unlike other infinite sums, like 1/2 plus 1/4 plus 1/8 plus 1/16, which neatly converge to 1, the harmonic series diverges, but it does so at a pace so slow, so patient, that it almost seems to pause. If you wanted the sum to reach 10, you'd need more than 12,000 steps. To reach 100, you'd need more than 10 circumflex 43 steps, a number so huge it dwarfs the number of atoms in the universe. Infinity lies out there, but it hides behind a wall of glacial growth. Think about what this means. The infinity ladder. Paradox isn't just about numbers. It's about the limits of progress, the psychology of the impossible, the nature of hope and frustration. Each new step feels like it should bring you closer to a destination, but in reality, the destination retreats faster than you can chase it. You're trapped in a loop. The more you add, the more you realize you'll never arrive. There's an almost cruel lesson here about the nature of infinity itself. We think of infinity as a place, a destination, a thing you could reach if only you had enough time or patience. But infinity isn't a place, it's a process. It's the act of always adding, always moving, never stopping. The harmonic series forces us to face this truth. You can climb forever and never arrive, yet somehow you're always making progress. It's a journey without a terminus, a story without an ending. Let's look at some analogies. Imagine filling a glass with water, but each time you pour, you add half as much as before. At first, the glass fills rapidly. Then, with each new pour, the water level creeps up more slowly. Eventually, you realize you'll never overflow the glass. That series converges, a finite limit. But in the harmonic series, you never reduce the fraction quite enough for the process to finish. Each new drop, however tiny, still counts. The glass will always inexorably overflow, given infinite time. Now, imagine an ancient king rewarding a wise man with gold coins, promising, "I'll give you 1 coin today, then 1/2 tomorrow, 1/3 the next, and so on, for as long as you live." The wise man would never become infinitely rich, but his fortune would grow without end, always inching upward. This slow divergence is so counterintuitive, it unsettles even seasoned mathematicians. But what does this mean for us outside the world of numbers? The infinity ladder. Paradox is everywhere in real life. It appears in physics, in the way certain systems accumulate energy or entropy, slowly, relentlessly, never quite stabilizing. It echoes in psychology, where the search for meaning, knowledge, or perfection is never truly finished. Every answer leads to a new question, every solved problem to another, smaller challenge. Even in philosophy, the paradox whispers a profound truth. Eternity is not a place to reach, but a horizon to chase. Our lives, our ambitions, our dreams, they grow and evolve, but they never complete. There is always another step, another challenge, another hope on the ladder. The infinity ladder teaches humility and maybe a strange kind of comfort. It says, you don't have to arrive to make progress. The journey is real, the growth is real, even if the finish line remains forever out of sight. But here's the deepest cut of all, the infinity ladder. Paradox hints that measurement itself is limited. Can eternity be measured without ending? Can progress be meaningful if it never completes? The harmonic series says yes and no. It invites us to dance on the edge, to appreciate every step for what it is, not for where it leads. So the next time you find yourself struggling toward a goal that always recedes, or chasing an ideal that never quite arrives, remember the infinity ladder. Remember that in the infinite there is meaning in motion, depth in the chase, substance in the unending. The ladder may have no top, but every rung is real. Every step is a part of your story. In the world of the infinite, the journey is the destination, and the paradox is the lesson. The irrational repetition illusion. Imagine a number that stretches out forever, digit after digit, a cosmic river of numbers flowing to infinity, never pausing, never circling back, never settling into a rhythm. This is the world of irrational numbers. At first, the idea seems simple. An irrational number is just a number that can't be written as a ratio of two integers. But peer closer, and a strange paradox emerges. A paradox that has haunted mathematicians and philosophers for centuries, that blurs the line between order and chaos, between the fabric of the universe and the static of pure randomness. This is the illusion of irrational repetition. Take pi. Most people learn it as 3.14 comma, the magic key to circles. But if you keep going, the digits never repeat. 3.141592653589793233846. On and on. Each decimal place revealing something new, something unexpected. Pi isn't just long, it's endless. The same is true for other famous irrationals like e or the square root of 2. Their decimal expansions twist out to infinity, without ever doubling back into a repeating pattern. No matter how far you search, you'll never find a simple block of digits looping back on itself. But here's where the illusion begins. There's a wild idea that hides in the depths of these numbers. Despite never repeating, their digits may contain every possible finite pattern. That means, if you search long enough, you'd find your birthday, your phone number, the works of Shakespeare, the code to every possible computer program, the genetic sequence of every living being, and even this very script you're listening to, hidden, scattered somewhere in the infinite dust of digits. It's like a cosmic lottery. Every possible sequence waiting to be found, if only you had forever to look. But how can that be? How can something that never repeats hold within it every possible repetition? The answer lies in the idea of normal numbers. A normal number is one where every finite string of digits appears somewhere in its expansion with the right frequency, purely by chance. So, in a normal number, the universe is encoded as noise. But here's the twist. Mathematicians still don't know if numbers like pi or e are truly normal. We suspect it, because random samples of their digits seem to contain every pattern, but no one has ever proven it. Every digit we check, every pattern we find only deepens the mystery. Think about it. The idea that an infinite, non-repeating sequence could encode every possible message, every possible reality, is both comforting and terrifying. It whispers to us that there is order inside chaos, that every story is possible if you search deep enough. Yet, it also means that most of what you find is just static, pure randomness, no meaning, just accident. If you could decode the digits of pi as letters, you could find the history of humanity, or utter nonsense. Both exist, tangled together, inseparable. Now, imagine building a machine that searches the digits of pi for secret messages. Every so often, it finds something astonishing, a sequence that matches the beginning of Hamlet, or the chemical formula for water. But look again. Almost every other pattern it finds is meaningless, junk, static. The information is there, but it's buried in endless white noise. It's the infinite library of Borges, every book ever written and every book that could be, but almost all of it is unreadable madness. So does an irrational number encode the universe? Or is it just random dust? The truth is, both ideas collide in a dizzying illusion. The digits are a mirror of what we bring to them. Order if you look for it, chaos if you step back. They are the fabric of randomness so profound that it can accidentally build all possible order, purely by accident, given infinite space. It's like looking at a wall of static and seeing the shape of your own face. Not because the static means anything, but because with enough chances, every image will flicker into view. Mathematicians are obsessed with these numbers because they seem to hint at a deep law of the universe, a law that says every possibility exists, but most of it is meaningless. Some people even claim that numbers like pi are the fingerprints of reality itself, cosmic blueprints hiding everything that was, is, and ever could be. Others argue that this is just our pattern-seeking brains tricking us, finding order in noise where there is none. Yet, consider this. Your own DNA is just a sequence, a code billions of letters long. In theory, the digits of pi somewhere encode your exact genetic code, atom for atom, and every variation you could ever be. The same is true for every song, every novel, every heartbreak, every victory. Infinity allows for all possibilities, but it promises none. It is the ultimate stage for meaning and the ultimate graveyard of nonsense. When you look at an irrational number, when you watch its digits spinning out endlessly, you are peering into a paradox, a world where nothing repeats, yet everything happens, if only you look deep enough. It's the universe as a never-ending shuffle, every outcome both inevitable and impossible. So, the next time you see pi printed on a t-shirt or recited by a math prodigy, remember, those digits are not just random. They are the very edge between chaos and meaning, a reminder that infinity is not empty, but full of everything, and nothing at all. The irrational repetition illusion is not a trick of numbers. It's the truth at the heart of reality itself. Will you see the pattern or just the dust? The answer, perhaps, is both. The pi inside, everything. If I ask you to imagine the concept of chaos, unpredictable, wild, infinite, refusing to fall into any pattern, what image forms in your mind? Maybe the swirling arms of a distant galaxy. Maybe the hidden tumble of a storm at sea. Maybe the raw, infinite digits of a number that never repeats, never ends, and never settles into a predictable rhythm. That number is pi, 3.14159266535, and so on, forever. But what if I told you that this infinite patternless chaos isn't just abstract or locked away in mathematics textbooks? What if I told you that pi is woven into the fabric of reality itself, hiding inside every wheel, every ripple in water, every spiral in a sunflower, and every orbit of every planet? And yet, despite being everywhere, pi remains untamed, unpredictable, and, in its own way, a fingerprint of nature's most mysterious side. Let's start at the surface. A circle. The kind you draw with a compass, or see in a clock face, or trace with your finger around the rim of a glass. The definition of pi seems simple enough. It's the ratio of a circle's circumference, the length all the way around, to its diameter, the distance across. No matter how big or small your circle, the answer will always be the same, a little over 3 times as long around as across, pi. But try measuring it perfectly, and the universe laughs in your face. No matter how fine your ruler, no matter how delicate your calculation, you'll never reach the end of pi's digits. It never repeats, never falls into a cycle, never reveals the secret of its next number. It's as if circles themselves are built on a foundation that can never be fully known. Yet, paradoxically, pi is everywhere. Engineers use it to design gears so smooth they could roll for centuries. Mathematicians use it to map out the path of a thrown ball, the ripples that expand in a pond, the way waves move through the air to carry sound to your ears. It's there in the equations that describe the curvature of space-time, the math of black holes, the bending of light, even the shape of the universe itself. If you could zoom out from your own life to look at the dance of planets around the sun, you'd find pi in every orbit. If you zoomed into the spiral of a snail's shell or the swirling heart of a hurricane, you'd find it again. Pi is both everywhere and somehow nowhere you can ever pin down. It gets weirder. Take the world of quantum mechanics, the realm of particles so tiny they barely exist as anything more than probabilities. When physicists want to describe the chances that an electron will tunnel through a barrier, a phenomenon so counterintuitive it seems to defy all logic. They use formulas with pi embedded inside. When astronomers study the echoing background radiation left over from the Big Bang, pi emerges in the statistics that describe the fluctuations in that ancient light. In other words, even the most cosmic, unfathomable scales are measured by the same number that tells you how far it is around a pizza. But the mystery deepens even more when you look at pi's digits. Unlike rational numbers, which eventually repeat or terminate, pi never does. Its digits go on forever, random, patternless, and unpredictable. In fact, if you look far enough into pi, you'll find every possible sequence of numbers somewhere inside it. Your birthday, your phone number, even an encoded image of the Mona Lisa. Mathematicians suspect all of it could be hidden somewhere in the infinite expansion of pi's decimal places. Yet, no matter how far you go, the number never falls into a loop. It's pure mathematical wilderness. Chaos inside order, order inside chaos. Yet, the world keeps using it. The ancient Egyptians used crude estimates of pi to build their pyramids, getting the proportions almost perfect without even knowing the real number. Archimedes in ancient Greece calculated pi to just a couple of decimal places by inscribing and circumscribing polygons inside circles. It took computers, centuries later, to crank out trillions of digits of pi, yet we still haven't found a pattern. Today, NASA's engineers use pi to plot the exact entry path for a spacecraft streaking through the atmosphere of Mars, knowing that a tiny miscalculation could mean burning up or bouncing back into space. The difference between survival and disaster, between landing a rover and losing it forever, is written in the digits of pi. But why should something so unpredictable be at the heart of everything predictable? Why does nature, with all its elegant regularity, depend on a number so wild and infinite? Imagine a universe without pi. Wheels wouldn't turn smoothly, orbits would wobble and collapse. The vibrations of sound and light would lose their harmony. Even the simple beauty of a bubble, perfect, round, balanced, would vanish, because the mathematics that shapes it would fall apart. Pi is the silent, hidden code that stitches the universe together, yet it always keeps its wildness, always hiding just beyond the reach of human certainty. Think about a gear turning inside a clock. The precision of timekeeping, the way one gear meshes with another to tick away the hours, all depends on circles, and, therefore, on pi, or the spinning of a planet, Earth turning on its axis, a day unfolding from sunrise to sunset, the seasons changing as our world orbits the sun. That cosmic rhythm, steady and ancient, is written in circles, in arcs, in orbits, everyone silently obeying the law of pi. Even in the most ordinary moments, pi is there. Every time you watch a pebble skip across a pond, sending out circular ripples, every time you see a rainbow arcing through the sky, a segment of a perfect cosmic circle, every time a wheel rolls, a pendulum swings, a planet spins, pi is silent, invisible, but always present. The ultimate paradox, infinity, hiding in the plainest things. So why is pi, in all its wild unpredictability, so perfectly embedded in nature? Some say it's because our universe is fundamentally geometric. Shapes, curves, orbits, cycles, all written in the language of circles. And circles inevitably call forth pi. But others see it as a reminder that the universe, no matter how much we try to measure and explain, will always hold secrets we can never fully reveal. Pi is both a key and a lock, a signpost pointing the way, and a warning that some truths can be known but never fully grasped. The story of pi is the story of humanity's search for meaning inside the infinite. We carve its digits into the memory of supercomputers, chase its expansion through the most advanced mathematics, and find it again in the everyday world around us. Yet, no matter how deep we look, it remains forever mysterious, forever just beyond our reach. Every circle is an echo of pi's endlessness. Every orbit is a signature of its logic and its wildness at once. So, the next time you see a circle, a sphere, a ripple, or a gear, remember that inside it lives an infinite irrational number, a chaos so profound that it never ends, yet so orderly that it keeps the universe from falling apart. Pi is the paradox inside everything, endless, unpredictable, yet essential. It is the fingerprint of chaos, quietly structuring the cosmos. It's the proof that nature's most essential secrets are always a little bit wild, a little bit unknowable, and forever out of reach. And that's why the universe, for all its beauty and order, always contains just a little bit of mystery. Pi is the code and the riddle written into the heart of everything. The Gödel number infection. Of all the mathematical viruses that have ever infected human thought, none is more disturbing, more beautiful, or more existentially haunting than the one discovered by Kurt Gödel in 1931. This is not a virus that attacks your body or a bug that corrupts your computer. This is a virus that slips silently into the heart of reason itself. It nestles inside the architecture of logic, at the core of everything we call certain. And once it takes hold, it guarantees that no matter how perfect your system of logic, no matter how hard you try, there will always be truths you can never reach. Always doors you can never unlock, riddles you can never solve, even if you have every key that mathematics has ever forged. This is Gödel's incompleteness theorem, and tonight we're going to let it infect us. Let's begin where all good infections start, with a promise. Imagine a world where mathematics is flawless, where every true thing can be proven, every paradox dissolved, and all contradictions banished. Early in the 20th century, mathematicians believed such a paradise was possible. They dreamed of creating a system, like an unbreakable fortress, where all of mathematics could be built from a few simple rules and axioms, as clean and precise as clockwork. David Hilbert, the leading prophet of this vision, declared, "We must know, we will know." In this era, math was the bedrock of reality. It wasn't just about numbers, it was about certainty, about knowing for sure that 2 plus 2 will always be 4, that geometry can describe the universe, that logic itself can never betray you. But like every paradise, this one harbored a hidden snake. That snake was self-reference, and it slithered in through a door that logic itself had built. If you want to understand Gödel's infection, you first have to imagine how mathematics and logic actually talk about themselves. Imagine a library that contains every book ever written. Now, somewhere in that infinite library, there's a book that lists all the books that don't list themselves. But should it list itself or not? If it does, it contradicts its own title. If it doesn't, it still does. This is the paradox of self-reference. And mathematicians thought they could avoid it by making their systems airtight, banning all the weird, looping statements that twist language against itself. But Gödel saw further. He realized that even the purest mathematics couldn't wall itself off from this kind of recursion. It would always sneak back in, no matter how you tried to keep it out. So Gödel began with arithmetic, the bedrock of mathematics. He found a way to encode statements, proofs, and even entire logical systems as numbers. This was Gödel numbering, an ingenious way of translating logic into arithmetic. Suddenly, statements could refer to themselves, using only the language of numbers. Imagine a number that encodes a statement about numbers, including itself. It sounds innocent, but it's a kind of logical time bomb, because now you can create statements that say things like, "This statement is not provable." Not this sentence, not this phrase, but a number built from pure arithmetic that encodes the idea. You will never find a proof of me within this system. If you could prove this statement, your system would be inconsistent. It would prove something false, but if you can't prove it, then it's true, but unprovable. Either way, the dream of completeness collapses. Let's go even deeper. Imagine you're in a perfectly constructed maze. You have a map of every path, every dead end, every escape. You are certain that you can find your way out, if you just search long enough. But Gödel proved there are doors in the maze that are invisible, walls that don't appear on any map, exits that exist but can never be reached from inside. No matter how far you go, there are truths about the maze you will never discover, not because you aren't clever enough, not because you haven't tried every method, but because the rules themselves contain a virus, an incompleteness that is woven into their DNA. Let's bring this down to a single, concrete example. In arithmetic, there are true statements about numbers that cannot be proven using the rules of arithmetic itself. For instance, statements like, "This statement cannot be proven in Pinot arithmetic." If you could prove it, your system would become inconsistent, capable of proving anything, including falsehoods. If you can't prove it, then it's true, but you're forever locked out from reaching it. It's as if mathematics is whispering, there is more truth than proof. There are realities beyond your reach. Imagine you're trying to write the ultimate book of everything, but as soon as you declare it finished, a new blank page appears, always just out of reach, always taunting you with one more mystery. The implications are staggering. For every consistent logical system complex enough to describe arithmetic, there are statements that are true but unprovable within that system. This is not a trick of language, not a glitch to be patched, but a fundamental feature of logic itself. It means no system can ever capture all mathematical truths. There will always be shadows, always be blind spots, always be a deeper layer of mystery. Hilbert's dream was shattered. Certainty had a crack running through its core. Gödel's theorem doesn't just haunt mathematics. It spreads like a virus into philosophy, computer science, and even the way we think about consciousness and reality. Alan Turing, inspired by Gödel, proved the halting problem. There is no algorithm that can decide, for every possible computer program, whether it will eventually stop or run forever. Some questions, even in the pure land of computation, are undecidable. Some truths, even in a world built from logic, can never be captured by logic. The infection is universal. It means that when you build any system, even one designed to answer every question, there will always be questions it cannot answer. Now, pause and consider the consequences. If logic cannot contain all truth, what about reality? Are there aspects of the universe forever hidden from us? Not because we haven't found the right experiment, but because no experiment can ever reveal them. Are there facts about existence, consciousness, or even your own mind that cannot be proven, cannot be known, cannot be brought into the light of understanding, no matter how much we advance? This isn't just a mathematical curiosity, it's a deep existential riddle. It suggests that every system we trust, every map we draw, every theory we build, is infected from the start. The foundation itself is incomplete, and always will be. Let's take one more step into the darkness. Suppose we try to patch the hole. Maybe we add new axioms, new rules, new ways of proving things. But Gödel's virus is clever. With each new patch, the infection just moves deeper. For any new, richer system, there will always be true statements it cannot prove. No matter how high you climb, the clouds of incompleteness rise above you. It's as if truth is an infinite mountain, and every time you think you've reached the summit, you look up and see a new peak above the clouds. You might be tempted to despair, to imagine that nothing can ever be known, that everything is relative. But that's not what Gödel showed. He didn't say logic is broken. He didn't say truth is impossible. He proved something subtler and far more profound, that truth is always larger than proof, that reality is always deeper than certainty, that no matter how far you go, how deeply you reason, there will always be mysteries beyond the horizon, true things that no system, no mind can ever fully grasp. And yet, it is this very incompleteness that makes reality so endlessly rich. It means there are always new questions, always new truths, always new frontiers for curiosity and wonder. Logic cannot lock up the universe in a cage. Truth will always slip through the bars. And as you listen to this, as you contemplate the viral beauty of incompleteness, remember, every system, every story, every mind is infected with a little bit of Gödel's magic. There is always more to discover. There is always more than can ever be said. And maybe, just maybe, that is the source of all meaning. So the next time you feel certain about math, about science, about life, remember the invisible virus in the heart of certainty. Remember Gödel's infection, because it's not a weakness. It's the secret engine that keeps us searching, wondering, and alive. And that is a truth no system will ever contain. The set that eats itself. Imagine walking into a library so vast it contains every book ever written, and then some that have never been written at all. Now, somewhere in this infinite library, there's a curious book. Its pages describe every book in the library that does not mention itself. You open it. Does it mention itself, or doesn't it? If it does, then it shouldn't. If it doesn't, then by its own rule, it must. That's the taste of a paradox so sharp it almost bites you. Russell's paradox, the set that eats itself. This isn't just an intellectual game. It's the moment in mathematics and logic where a question detonates beneath the foundation, and the shockwave never stops. At its heart is a deceptively simple idea. Can we define a set? Just a collection of objects, anything we can imagine, that contains all sets that do not contain themselves. Pause and let that echo. A set that only contains the sets that do not contain themselves. Let's call this set R. Now, the question, does R contain itself? If it does, then by its own definition, it must not. If it doesn't, then by its definition, it must. You are caught in a logic loop, spinning around the center of a mathematical black hole. This is not some distant, abstract puzzle for logicians with nothing better to do. This is the hole in the bottom of reason itself, the place where mathematics, set theory, and even language threaten to collapse. To understand why this matters, let's zoom out and talk about sets. In mathematics, a set is just a collection of objects, numbers, people, socks, or even other sets. Most sets are innocent. The set of all odd numbers, the set of all cats on Earth, the set of all prime numbers less than 100. But then the 19th century rolled in, with mathematicians chasing the dream of complete logic, a world where every mathematical truth could be captured in airtight, perfect language. Enter naive set theory. The idea was, if you can describe a collection, you can make it a set, the set of all blue things, the set of all sets that contain themselves. Why not? This was the vision of Georg Cantor and his followers, a universe built from sets, each stacking on top of each other, building complexity from pure logic. But in 1901, Bertrand Russell found a crack that split the dream in two. Let's try a simple example. Suppose we have a barber in a town who shaves all and only those men who do not shave themselves. The question is, does the barber shave himself? If he does, he shouldn't, because he only shaves those who do not shave themselves. If he doesn't, then he must, because he shaves all those who don't shave themselves. The barber's dilemma is just Russell's paradox, lurking in everyday clothing. No matter how you twist, you can't escape the contradiction. But the real terror comes when you realize this isn't just a trick of words. It's a wound in the structure of logic. If you allow the set of all sets that do not contain themselves to exist, you open the door to contradiction, where anything, literally anything, can be proven. The laws of mathematics start to break down. Consistency crumbles. This is the paradox that made Russell weep and forced all of mathematics to rebuild its foundation. Before Russell, mathematicians believed that sets could be freely defined, as long as you could describe them. But Russell's paradox is a monster that eats its own tail. By trying to define the set of all sets that do not contain themselves, you create a self-referential loop. If it contains itself, it shouldn't. If it doesn't, it must. There's no escape, only endless oscillation. Let's make this more vivid. Imagine a giant register of clubs. Each club has its own rules for membership. Some clubs let anyone join. Some only allow left-handed musicians. Now, imagine there's a club called the Club of Clubs That Don't Admit Themselves. Its only rule, it only admits clubs that do not include themselves as members. Should this club admit itself? If it does, then by its own rule, it must expel itself. If it does not admit itself, then it meets the criteria and must let itself in. Round and round, logic burns itself to ash. You might wonder, isn't this just wordplay? Can't we just avoid such nonsense sets and continue? That's what mathematicians thought at first, but the rot was deeper. This paradox lurked everywhere self-reference was allowed. If mathematics allowed definitions that reference themselves without limit, the whole system risked explosion. This wasn't just a mathematical embarrassment, it was a foundational disaster. Russell's paradox shattered the dream of a perfect, complete mathematics built from simple rules. It exposed the dangers of unrestricted comprehension, the rule that says any property can define a set. You can't. Some collections are too wild, too hungry. They eat themselves, and in the process, devour the system meant to contain them. The aftermath was nothing short of a mathematical revolution. Mathematicians scrambled to patch the hole. New systems were invented. Set theory had to become stricter. The most famous solution was the Zermelo-Fraenkel set theory, which introduced rules to prevent bad sets from forming. Now, sets can only be built step by step, from earlier, simpler sets, not from all possible descriptions at once. The club of clubs that don't admit themselves? In this new world, it simply can't exist. It's outlawed by the very fabric of mathematics. But the ripples didn't stop at set theory. Russell's paradox inspired logicians like Gödel, who proved that any system complex enough to describe arithmetic will always contain true statements it can never prove, shadows of incompleteness lurking forever. The paradox also forced mathematicians and philosophers to confront the limits of formal reasoning. Language itself, it turned out, could turn cannibal. Anytime you allow self-reference without guardrails, you risk birthing monsters. You see echoes of Russell's paradox everywhere. In computer science, the halting problem asks, can you write a program that decides whether any other program will ever stop running? Turing showed this is impossible, and the proof dances in the same logic loop. If you could write such a program, you could feed it itself and ask, will you halt when asked about yourself? The contradiction erupts again. In philosophy, self-reference is the engine behind classic paradoxes. This statement is false. If it's true, then it's false. If it's false, then it's true. These paradoxes haunt our attempts to build airtight, logical worlds, reminding us that self-reference is a knife edge, capable of both creation and destruction. Russell's paradox is not just a historical curiosity. It's the hidden fracture at the heart of logic, mathematics, language, and even consciousness itself. Every time you define a system, you must beware. Somewhere, a set might be lurking that wants to eat itself and take you with it. So, the next time you think of mathematics as a cold, emotionless domain, remember the set that eats itself. Remember the horror in Russell's discovery. The realization that even in the purest logic, there are questions that explode into contradiction, self-reference that mutates into madness. Even the foundations of knowledge tremble before a paradox, one that begins with a simple question and ends by devouring everything. We build our worlds on logic and reason, but in the cracks, paradox waits, patient and hungry. The set that eats itself is always out there, just beyond the edge of understanding, whispering its unsolvable riddle into the night. And somewhere, Russell still weeps, not just for the paradox, but for the truth it reveals about all human knowledge, that no matter how perfect our logic, the universe always reserves the right to surprise us, and sometimes to swallow itself whole. The Turing halting trap. Imagine this. You're sitting at a computer, surrounded by lines of code that twist and sprawl like a living labyrinth. Your goal is ancient, primal, the dream of ultimate control. You want to know, before ever pressing run, whether this machine will do what you want, or fall into an endless, unbreakable trance. At first, this sounds simple. Write a program, check its logic, and predict. Will it halt, or will it run forever? This is the halting problem. A paradox so deep it split the mind of mathematics, rewired computer science, and, in its shadow, forced philosophy to look into the heart of all calculation and see the abyss staring back. Let's break it down. When you write a program, you often wonder, will this code ever finish? Or is there a bug, a hidden loop, a secret recursion that traps it for eternity? Could you write another program, a decider, a perfect oracle, that examines any program and its input and tells you in advance with total certainty whether it will halt or spiral forever? It seems so reasonable. After all, if you can run the program, you can watch what it does. But that's just it. What if running it is the only way to know? And that running could mean waiting longer than the universe has existed? Enter Alan Turing, the young, haunted mathematician who, in the 1930s, peered into this void and did something no one expected. He proved, not by calculation, but by logic, that this dream is not just difficult, it's impossible. There cannot exist any algorithm that, for every possible program and input, always gives the correct answer. Will it halt or not? The problem is unsolvable, and not because we lack imagination, but because the very nature of logic contains this dead zone, this unscalable wall. How did Turing reveal the impossibility? He invented a mental machine, the Turing machine. Imagine it, a tape, infinite in both directions, marked with symbols, and a head that can read, write, and move left or right, following rules encoded as the program. This machine is as simple as possible, yet as powerful as any digital computer or brain. If you can write an algorithm for it, you can write it for anything. Turing's genius was to ask, is there a program that, given the code for any other program and its input, will always predict in finite time whether the other program halts or loops forever? Suppose you claim there is such a decider, a mythical machine, let's call it H, that solves the halting problem. You feed H the description of any program P and its input 1. If P halts on I, H says halts. If not, H says loops. Now, Turing uses the decider to create a paradox. He writes a new program, call it Q, that takes as input the description of a program. RQ asks H, does R halt when run on its own code? If H says yes, Q goes into an infinite loop. If H says no, Q halts instantly. Now, what happens if you feed Q its own code as input? If H says Q halts, Q will loop forever. If H says Q loops forever, Q will halt. The logic eats itself. No matter what, H gives the wrong answer. The decider can't exist. Let that land. Logic itself, as strict and precise as possible, can be twisted into a contradiction by self-reference, a trapdoor in the floor of certainty. The halting problem is not a mere technical difficulty. It is a built-in boundary of the knowable. There will always exist programs whose fate cannot be predicted except by running them. And even then, you might wait 1 billion years and still not know if they'll ever finish. This is not just abstract math. The halting problem is the shadow lurking behind every software crash, every spinning loading icon, every AI whose actions might never resolve. If you write code, you know the feeling. Did I forget an escape condition? Is this recursive call ever going to return? Can I trust my logic? Or am I lost in the fog, the system working endlessly while the world outside keeps spinning? There are programs, shockingly simple ones, whose behavior we can never predict without running them out to infinity. Computer security exploits this. Malware that hides its payload in layers of conditional logic, triggers that only reveal themselves after billions of cycles. Some viruses disguise themselves as unsolvable logic puzzles, so no antivirus can ever guarantee in finite time whether the code will halt or not. Even modern software testing tools, static analyzers, formal verifiers, are haunted by this limitation. They can't guarantee to find every infinite loop or unfinishable calculation. To try to prove halting for all programs is to attempt the impossible. But the halting problem is even deeper. It's not just about code, it's about reality itself. Think about human minds. Are our thoughts like programs? If so, do we ever halt? Do we ever finish processing? Or do some ideas keep us trapped, looping forever in rumination, worry, or obsession? Some philosophers wonder if consciousness itself is an infinite loop, a self-reference that can never be resolved, a process forever running, never halting, always hungry for input, always afraid to stop. Turing's paradox is a mirror for the universe. In physics, some processes can never be fully predicted. In mathematics, some theorems cannot be proved or disproved by any finite procedure. In logic, some statements refer to themselves, twisting meaning into paradox. In computation, the boundary between what can be known and what can only be experienced, lived, or simulated, never predicted, runs right through the core. For a more vivid example, picture this. You write a program that asks a user for a number. If the number is 1, it halts. If the number is 2, it loops forever. But what if you write a program that asks another program to decide if it will halt, then does the opposite? You've constructed a liar's paradox in code, a digital version of "this sentence is false." Try to decide it, and your logic twists into knots. Even the simplest computers become battlegrounds of contradiction and uncertainty. There are practical consequences. Airlines, hospitals, banks, all run on software. They run simulations, tests, and code reviews, but they cannot guarantee every program will halt. There will always be edge cases, bugs, unanticipated inputs. The more complex the system, the more likely it harbors a hidden infinity, a process that will never resolve. This is why software fails in spectacular, unexpected ways. Not because engineers are careless, but because, at a fundamental level, perfect prediction is impossible. What does this mean for us? It means the universe, at its most logical, is still filled with mystery. There will always be boundaries, limits, places where knowledge and prediction break down. It's humbling and thrilling. The halting problem is a portal, showing us that even as we build machines to extend our minds, we will never achieve total certainty. We are forced to live, not in a world of perfect control, but in a world of risk, adventure, and unknowability. Alan Turing's insight was not just a technical discovery. It was a profound philosophical revelation. Not all questions have answers, and some answers can never be known except by living them out, step by step, line by line, in real time, possibly forever. Computation becomes philosophy. Running code becomes a metaphor for existence, a journey whose ending is always in doubt, whose meaning is found not in certainty, but in the very act of running, of exploring, of trying, and sometimes of never knowing. You can't predict if a program will halt. To know, you must run it. But to run it is to possibly never stop. The halting trap waits at the edge of every calculation, a silent reminder that not even machines, for all their logic and power, can escape the infinite loops that haunt the mind of creation itself. The cardinality explosion. You probably learned at some point that infinity means forever. That infinity is just a single endless thing, some mathematical dream stretching on, unreachable and identical no matter how you approach it. But that's a comfortable lie, a story that helps us sleep at night, tucking away the terror that comes from facing the true structure of reality. The truth is far stranger. Infinity isn't one size. It isn't a single mountain whose peak disappears into the clouds. Instead, there's a whole mountain range, with peaks upon peaks, stretching into a mist so thick not even imagination can pass through. There are infinities that fit inside other infinities. There are infinite staircases of infinite heights. Some infinities are bigger than others. Welcome to the cardinality explosion, the concept that shatters our deepest assumptions about number, order, and the very foundation of what beyond truly means. To see the beginning of this explosion, picture yourself counting 1, 2, 3, 4, and on. You can do this forever, at least in theory. Mathematicians call the size of this set, these whole numbers, one after another, countably infinite. There's no largest number, but every number has a place in line. You could, if you had forever, eventually count to any number you name. The technical term for this set size is a left null, or 0, the smallest infinity. But that's only the first rung on the ladder. Now, what about the even numbers? 2, 4, 6, 8. Couldn't you argue that there must be fewer of them than all the whole numbers? They're spread farther apart. Surely the set is smaller. But here's the twist. You can pair every whole number with an even number, 1 with 2, 2 with 4, 3 with 6, and so on, never running out on either side. That's the trick of infinity. Even if you throw away half the numbers, what's left is just as big as what you started with. Infinities can be equal, even when they seem unequal. But let's up the stakes. What if, instead, you consider all the fractions, every number you can write as one whole number divided by another? Suddenly the numbers swarm around you, dense as dust in a sunbeam, filling every gap. But still, shockingly, this infinite ocean is countable. With clever enough ordering, zigzagging through all numerators and denominators, you can make a list that touches every possible rational number. Infinity, but still aleph null. Here, most minds begin to relax. Maybe, just maybe, infinity really is just one flavor. Maybe everything endless is somehow the same. That's when Georg Cantor arrives. He's the mathematician who detonated the infinity bomb, the architect of the cardinality explosion. In the late 19th century, Cantor asked the forbidden question, are there infinities that are truly, absolutely bigger than others, not just in a tricky way, but in a way that can never be bridged? He found the answer lurking in the real numbers, the endless line of decimals between 0 and 1. If you try to list every real number, lining them up like soldiers, Cantor's diagonal argument slices through your list with surgical precision. Take the first digit of the first number, the second digit of the second, and so on, changing each digit just slightly. The result? A new number that is guaranteed to be missing from your list, no matter how you try to order it. The set of real numbers is not just bigger than the set of integers. It's a fundamentally larger kind of infinity. The reals are uncountable. No matter how long you count or how cleverly you zigzag, you will never touch them all. Cantor called this size the cardinality of the continuum, or simply C. So we have at least two infinities, countable and uncountable. But the explosion doesn't stop there. Mathematicians started wondering what lies between. Is there an infinity sandwich between the countable and the continuum? This is the notorious continuum hypothesis. Cantor himself never answered it. In fact, it sits at the heart of mathematics as a kind of spectral question, one that, as Kurt Gödel and Paul Cohen later proved, can never be decided within the standard rules of math. We can imagine, construct, and play with infinities of different sizes, but there are chasms between them we cannot cross with logic alone. Now, take a step back and try to comprehend what this means. Between 0 and 1, the reals form an unbroken fog of numbers, impossible to list or capture. But then, above the continuum, there are even bigger infinities. The set of all possible subsets of the reals, for instance, has a cardinality so enormous that the mind falters even to glimpse it. Every time you take the power set, all possible combinations of a set, you explode the infinity to a new, higher cardinality. This doesn't stop. The ladder keeps rising, rung after rung, each one infinitely higher than the last. Aleph 1, Aleph 2, Aleph 3, each a universe of its own. If you find your intuition buckling, you're not alone. This isn't just numbers, this is a warping of how we see possibility itself. The philosopher David Foster Wallace once called Cantor's discovery the most paradoxical and most beautiful in all of mathematics. It's the mathematical equivalent of discovering that space itself is layered with invisible, untouchable dimensions, that there are infinite galaxies, and then infinite galaxies of galaxies, and so on, forever. Let's ground this in something more concrete. Imagine a hotel with countably infinite rooms, the famous Hilbert's Hotel. Every room is full, but if a new guest arrives, you can still make space by moving everyone up one room. You can even make room for infinitely many new guests. But if an uncountably infinite set of guests arrives, there's no way to fit them in. The countable infinity, no matter how clever, is dwarfed by the uncountable. It's a boundary you cannot cross. In the physical world, the implications are haunting. In quantum physics, in cosmology, in information theory, we run up against the limits of countability and uncountability. Is the universe, at its deepest level, built from countable steps? Or is it a continuum, a fog with no gaps? If you believe the world is digital, you are comforted by countable infinities. If you believe it is analog, you stare into the uncountable abyss. And then, in the mind, the real crisis blooms. Human intuition is tuned for the finite, the manageable, the countable. We are built to tally, to order, to list, and to compare. But when you step into the realm of cardinalities, you have to abandon almost every tool evolution gave you. You can only stare, wordless, into a mathematical night sky dotted with infinities of every possible size, shimmering, unreachable, cascading upward in impossible hierarchy. But here's the final, devastating twist. Even within the uncountable, there are greater and greater infinities. Take the power set of the continuum, the set of all sets of real numbers, and you get a cardinality even larger than C. This process repeats endlessly. The infinite is not just a place you reach and stay, it's a staircase with no end. And yet, despite all this, every step, every jump, every explosion of size can be made as real, as rigorous, and as precise as the numbers you learned to count on your fingers. Infinity, it turns out, isn't a void or an abstraction. It's a landscape, alive with structure, shadowed by paradox, and dizzying in its scale. The cardinality explosion is more than a mathematical curiosity. It's a window into how reality can shatter our ideas, expand our boundaries, and remind us always that no matter how far we climb, there is always more beyond. And sometimes, the most infinite truths are the ones that show us how small we really are.